Okay, good morning, everyone. Please take one of the free seats. Next up, we have Pier Paolo Ippolito. He's a data analytics engineer at Swiss Re, and he has a Master of Science in Artificial Intelligence. He's also a writer for Towards Data Science and a freelancer consulting in data science, machine learning. So everybody welcome him, and he has a talk about paradoxes in data science today.
Hello, and thank you everyone for joining today. So as said, I'm Pierre, work at Swiss Re, and I'm also a writer about the data space, and I'm going to do this sort of projects on the side. And yes, can you hear me? Yeah, okay. Yeah, so and then apart from that, you can see I've collaborated with different companies and wrote articles, like for example with NVIDIA, and some articles have been published by Cornell for their courses, or by Kaggle by sharing online, say. And so, yeah, starting with the topic, we are talking about paradoxes today, and paradoxes are, to give an intro, are a class of phenomena that arise when, although starting from knowledge is not true, we derive some sort of logically unreasonable results. And nowadays, machine learning models, they are completely based on data, and they make inference on data, and therefore, if there are differences, for example, between the training and testing data, they can also be suffered like we do with a bit of cognitive paradoxes, basically. And one of the main techniques that can be used to try to understand more these paradoxes are, for example, modeling and simulations. And for understanding models, it's really important to remember that this quote from George Box, where it says that essentially all models are wrong, but some of them are useful, which is really important because models are always a representation of the real world environment, but they can never be one-to-one with the real world environment. And therefore, there are always assumptions or changes that they may not be able to capture over time. And it's important to know now, basically, that as for this first paradox, one of the main reasons why we use models, which are not related necessarily to machine learning models or deep learning models like they are today, is that we want to basically understand an environment and make predictions on that. That's why data science was developed, let's say. But at the same time, in not all the cases, we have data to start with. And if we don't have data, how can we perform data science? And one way to do this is basically to generate this data through simulations. And this can be much more common than we normally think. For example, if we consider a thought experiment and we say, okay, we are a data scientist and we're working for a local authority, and we're asked to create a way to try to optimize an evacuation plan for a city in case there is a natural catastrophe, like earthquake, volcano eruptions, and so on. Hopefully these things don't happen so often, so we don't have data about how to model this sort of situation. And therefore, what we do in this kind of situation is try to basically create a synthetic environment in which we model the situation, the people, the escape routes, and so on, and run simulations against them and generate data, which can then give us results on how to then make best decisions and generate policies from the government point of view. And this was also done, for example, during COVID. In fact, if you remember at the beginning of the pandemic, there was no data, no people knew how fast it was spreading, what was the cause of spreading, and the disease, and so on. And in order to perform this sort of analysis, there are two main approaches. One is mathematical models, and the other is process models. With mathematical models, we generate a set of equations and that summarize the relationship between different states, and then run them and generate some results. Instead, with process models, we handcraft the steps of the algorithm and the environment in order to then synthetically generate the results. And this can be used, for example, in many situations. For example, one of the most basic ones that we might know are related to Bayesian inference, where you can have priors for the environment, or Monte Carlo simulations for portfolio optimizations or things like that. These are all sorts of simulation techniques. And more complicated ones that are used nowadays, for example, relate more to, like, for example, doctor medical training in synthetic environments, or military operations in synthetic environments, and also epidemics and model threats for cybersecurity as well. And then, for example, once we got this data, you can then help governments or decision makers to basically experiment policies before actually apply them in the real world. So, for example, you could create a model to simulate COVID spreading, and you can see, okay, if I do a lockdown, what will be the results, how many that you expect less, and so on, before making an actual decision. And because these models are made and are crafted by us through either through mathematical equations or through elaborations of steps in like object-based modeling, then that makes them basically a sort of a white box-based approach compared to using just heavy models for deep learning and to solve a solution, let's say. And so starting with convolutional models, as I said, they are based on equations. So you can see basically we can design, for example, 3 sets of equations here for modeling epidemics development. And in this case, we see we have 3 equations, differential equations that runs against time, where we can run a simulation. And the first one can represent, for example, delta S, the people that are susceptible to a disease. The second one, the people that are infected. And the third one is the people that recover from it. And then you can see that there are different parameters that determines how people can move in different compartments. And each equation can then be represented by a compartment in a diagram, where we can see then how the flow of the people can move throughout the simulations, and what kind of probability there is between a person moving between one state and another, at what rate people are moving, if it's a fast rate or a slower rate, and so on. And once we run this against time, then we can see you get these sort of curves and analysis, which are also, for example, been shown during COVID by many governments. For example, the UK government started with the Imperial Research Study, started with a much more advanced version of analytical model like the SIR, and during conferences, during lockdowns and so on, they were showing actually these curves to show how their policies were trying to bring down the orange curve in this case, and basically, bring down the infected, the green curve, and then try to reduce the amount of people that would be suffering for that, let's say, and calculating the R value that you think can be estimated also through these simulations. Okay.
Closer, or you get up, because otherwise the streaming will get the. So if you can get this one, it'll be way better. Because the streaming will not. It doesn't work on the screen. Does not? No, we can only use this one. Okay. Because the audio there is quite low. Okay. So you either shout a little bit.
Okay.
Or probably you just have to go together.
Okay. Really close. Okay. Yeah. No problem. And yes, so the second approach is I was mentioning about is object-based models, and in this case, basically, we take sort of object-oriented programming approach where we create a class representing a person in the environment, and then give it different properties and parameters that can be played with. For example, you can obviously a position, a speed in which it moves, a direction, a certain age. How many, for example, days of rehabilitation has been going through after getting the disease, and so on. And then once run this approach, we can see that we can generate an algorithm, which can be generated by us for saying, I don't know, how for each day in the simulations we loop through the different individuals and what will be the probabilities and the radius in which you need to be close to another individual in order to get actually infected, and so on. And running this, then you see that we get again, similar type of curves, but at this time, instead of using actual mathematical equations, we generated with our own understanding of the process and environment. And because of that, we can also make them also multidimensional. For example, before we were running against just time. Now we also run them against space, and we can see the different individuals in a 2D space moving around and getting a more clear view on the simulation itself. And then, if you're interested, there are also other approaches which you can use in order to make these simulations yourself. So in this case, I sort of hard code them with myself and do it from scratch. But there are also packages in Python like Mesa, or also Hash, which is a framework which you can use in order to create the simulations, or enterprise level tools like AnyLogic or Blender that you can use as well. And now we can quickly show you an application I developed on this, which was developed on AWS, which is using Streamlit and has also Docker support, and is freely available on GitHub if you want to clone it, start it, or do anything with it. And yeah, so I can quickly walk through the application here. So you can see here, this is the main tab where you can get the welcoming page, and then here we can run the different simulations. And for example, this one is based on agent-based models. You can see that you have parameters for the population size, the death probability, the concat region which you need to be within in order to gets infected by someone else, and for example, also the average population age, which can infect how heavy you can be affected by the disease, and then you can see that you can actually get these simulations and run them and see how the individuals move in a 2D space and how this affects the curves, which then get generated. And then you see you can get reports and different sort of analysis. And starting from this, then you can also try to test policies. For example, you can see, okay, what if now we decided that when someone gets infected, needs to immediately run to a specific location and isolate and try to not get in touch with anyone else. And in this sort of scenario, you can see that basically we can do, for example, track and tracing, and you can specify this sort of also community parameters. So, for example, if the community is static, if it's dynamic, for example, simulating a lockdown or no lockdown environment, and if there are different levels of communities. So, for example, if it's just a small town in the middle of nowhere, or if it's a, I don't know, 4 towns and a big center at the middle, and people moving across different towns and so on. And you can see here, then you see you get some sort of different curves with the same parameters. You can see there is this red box at the bottom, and every time that someone gets infected, immediately runs into this red box quarantine area in order to not get in touch with anything else. And you can see here, then you have different type of scenarios, like with 8 communities, 4 communities, and so on, to try to get more complexity and improve the simulation analysis the same. And apart from that, then you can see this is agent-based simulations. But coming back to mathematical models, we can also create the more advanced version of the 3 equations I showed you before. And instead of having just 3 equations, you can see you can add more states. For example, one for time-limited immunity, so people that get infected, they recover. Then for a time period, they are immune to the disease, and then after a while, they become again susceptible and can be infected again. And people that get vaccinated, for example, and don't get reinfected again, and so on. And then you can see you can play with this and get, again, same sort of simulations and create more complicated equations on top of that to make it more realistic as possible. For example, I think the imperial model that was used in the UK had more like 30 parameters or something like that. For example, these are 6, 7 parameters for a moment, just to provide a quick demo, let's say. And yeah, then there is much more on the actual presentations there. But you can feel free to explore it in your own time, because we are limited today for the time of the presentation. And yeah, so this was created from scratch using Python and using Streamlit as an interface, and Plotly for also plotting. But at the same time, you can see there are also built-in tools and libraries that are designed specifically for creating models and simulations, like this one, which is Mesa, which is shown now on the screen. And with Mesa, you can create, for example, this is a 3 forest fire simulation. So you can see that basically we got a tree that caught fire, and based on the density of the forest, you can see how this can then spread across the forest, and then how people can try to design to space out a bit the trees so that the event gets isolated and doesn't spread around constantly, let's say. And then as well, there is also a more enterprise tool, which is Hash, which provides you with built-in capabilities for visualization as well here. And in this case, you can see that you can then design more complicated graphs and these are provided out of the box, more or less, for many scenarios. So, for example, there are also simulations for airport management or supply chain optimizations and things like this that people can just create and provide as template to the community for other people to use it, basically. And coming back to a more recent sort of approach, we can see that basically during the last few years, there has been also the development of large language models, which have been becoming more and more popular nowadays. And this can be used also for actual simulations now. For example, during the last month alone, I've been designing different papers, like, for example, this one with generative agents for human interaction, where basically we have a sort of a Sims simulation, where, as you can see in the image, you have different people basically living in different flats and interacting to each other. And each of these person basically is a language model, and they just interact with each other, organize things, do things, and basically create a proper Sim simulations, basically. And moving forward, then there has been also other applications, like, for example, language models for simulated economic agents, where basically you simulate, I don't know, language models impersonating companies and decision makers in the companies, so that they can then decide what kind of policy to apply, and how the language model responds, and so on. So in this case, basically, you have, instead of having just one model, so like GDP talking with you, you have multiple models talking each other and trying to achieve greater things and narrow down the scope. And that's why, for example, also Alex Carpati, which was the head of AI at Tesla, also said that auto GDP will basically be the next frontier probably of prompt engineering, because instead of you having to get prompt really crafted to get the results, you will have two agents which are have an antagonist role, let's say, basically, sort of a client-customer face approach, and they talk each other to get you then the response that you actually want in the first place, so without you being in the loop to try to get GDP to do whatever you want. And finally, also Salesforce did a nice, interesting research about it, which was based instead on reinforcement learning, in this case for the AI economist. So basically having a simulation environment where these AI models for using reinforcement learning were testing different policies and seeing, for example, if capitalism or libertarism or other type of approaches to economy were giving better results in the long term, in the short term, and so on, to get better insights on that. And then going forward, you can see that the second paradox I wanted to introduce today is the Simpson paradox. And in this case, basically, the Simpson paradox is a phenomenon in probability and statistics where a trend that appears to appear in several different subgroups of data, but disappears or completely reverses when you look the sample in its whole completity. So, and this is really interesting because basically that means that you can get things that you completely don't expect. So, for example, in this case, you can see here that there is a simple thought experiment where we are trying to basically examine how cholesterol levels can depend on how much you exercise, basically. And here, basically, you can see that for this experiment, we decided to divide the sample into different categories: people that are under 60 and people that are over 60. And you can see that in both cases, when we see under or over 60 patients, we can see basically that as we increase the number of hours that people exercise, the cholesterol levels of the people go down. But then when we actually add the two samples together, we can see that then the correlation flipped. So instead of being negative, it becomes positive. And that's just because we consider the whole sample as a totality. And this obviously doesn't sound right to us. And there can be different reasons for this. So, for example, one approach we can take is basically to try to understand if there is any sort of hidden variable which we are not accounting for in this analysis, which might be causing cause-effect relationship flips there. And therefore, it's important, for example, in this case, to consider the age, obviously, because as you increase with age, then cholesterol levels tend to naturally increase. And if you see that here, you can see that basically you get perfect correlations between under 60, over 60, and the sample together for age. And therefore, you can see basically that this was the reason why the correlation got flipped there. So in this case, going forward, let's say, you will basically do that if you perform the same analysis of the slides I showed you before, here, but you keep the age as a constant variable, then you will see said that when you add the samples together, everything will look perfectly fine. And that's a case where the Simpson paradox can appear, say. And another case is the accuracy paradox. In this example, basically, we need to basically bear in mind that every time we do an analysis, we always think that going deeper will lead to better results, but that's not always the case. In fact, there will be circumstances in which having sort of the bigger picture can probably help in the long term. And that's important because you can see that basically whenever we try to create machine learning models, we always try to optimize some form of metrics. But if we don't optimize for the right metrics, or if we over-optimize for that a simple metric, then we will just get worse results in the long term, and with the appearance of good results in the short one. And this can basically summarized as a accuracy paradox, where basically we overestimate for a sort of metric and get really good accuracy for some training or times and so on, but then in actual application is not so good. And this can be also seen, for example, when if we create a model here for here having house prices and try to predict what is a house price depending on the number of rooms. If we train a model for the Italian market, and we push it to the maximum, this model will perform good for the Italian market, but then if you try to test it against the Spanish market, will probably perform much worse than a model that is less overfitted to the regional model. So if you do that simple linear regression, it probably will work well for many markets. Instead, if you do a really deep learned model, it will go well for the Italian market, but will go bad for other markets, let's say. And this can also be seen, for example, also in when you do classification type of models, especially when you have an unbalanced set of data, where we try to just optimize for either for positive or for negatives and so on, and then the model doesn't perform too well. And this can also be summarized by this quote by Charles Goddard, when he says, when a measure becomes a target, it ceases to be a good measure, which is really important to remember in this case. And this can also be seen also by, for example, the Pareto principle, where you see if you focus really on the 80% important things, you can always get really good results fast, instead of trying to optimize for the leftover 20% that might take ages to try actually to get, and then might not work well in other type of scenarios from the one originally planned. And another paradox I wanted to introduce quickly today is the learnability Gödel paradox. And in this case, basically, Kurt Gödel was a very important scientist of the last century, and he basically emphasized how it can be, how math can have some sort of limitations, and how in some cases it can be impossible to make extrapolations about a population from a sample. And if this is the case, basically that means that any sort of machine learning or data science model will never be probably good or reliant about, and you can generate AGI, because in every case, basically, we just work on samples data. We never work on entire population of data. And this, therefore, can greatly limit our impact that we can have in the real world using just data as an input. And that's why, for example, also Julia Perl or other scientists really pushing forward to using causal AI, which is based on rules and relationship instead of just data. So to get basically same sort of results, but with much less data, make the models much less data dependent, basically. And the last one I want to cover today is the law of unintended consequences. And in this case, basically, you can see that we always strive to create really complicated models or really complicated infrastructure to get to cover any sort of edge case or anything. But this can at times make things more complicated, because that extra complexity makes more difficult then to understand when things might go wrong. And therefore, you see a domino effect that you are not really understanding what might be the source of a problem, of a bug, or anything, if the different pieces are not independent of each other and correctly connected to each other, let's say. And this can be also really important, especially nowadays with the advent of GDPR, where you have the right for explanations clause, and where people can demand to have an explanation of why some things don't work or why some decisions were made. And if you are making these sort of really complicated systems, which can be more difficult to extrapolate in design, then that makes more difficult then for you to actually provide reasoning and explanations to end users or customers, let's say. And so going on to the conclusion, basically in this presentation I provided some common paradoxes, but obviously there are way more apart from this. And this can be due, for example, some example here are the friendship paradox in network analysis, where this paradox can explain you why your friends on average have more friends than you do. And the Bergson paradox, Price paradox, Morolla paradox, Berde paradox, and so on. You can see there is a really long list. And if you have anything else that you want to add on top of this list, just let me know. I'm curious always to learn more about this. And so if you're interested in learning more about this topic, there are these 3 resources I found really useful, which is the Book of Why by Julia Perl. Julia Perl wrote many different type of books about causality, and the Book of Why is probably one of the most famous ones, but you are free to also explore other works that he did about this. Or also the Model Thinker, which is a more general book, and it just talks about different types of models, which nowadays are mainly associated with AI, but can be Bayesian models or any type of more historical models as well that has been ever developed during the past couple of centuries. And also thinking in system is quite interesting, where you try to connect models to each other and see how this can affect end results, for example, by cascading models or creating bigger pictures type of analysis. And that's it for me. So thank you very much. If you have any questions, just feel free to reach out.
Yes. Thank you for this very interesting and visual talk. We have some questions on Slido. If you have any more questions, feel free to add them to the Slido room in Risotto. The first question is, when you showed the plots about infections, the lines straighten out after some time. Why is this?
Which plot?
About infection, like the first plots you showed. I think it was in the online browser.
Because why it goes straight after
Yes,
some time?
exactly.
Because obviously we cover the whole population, basically. Imagine that I had a population of 500 individuals, and in fact, if you, for example, if you see here, if you add the numbers of the different lines at the tops, you'll then see that you get the maximum number of people. For example, here in this case, you have 60 people in the regional population in blue, and they go down. And then after it topped, and it becomes a straight line because obviously some people died, so that they can be moving between states, and some people got recovered, and they can't be reinfected in the simulation, basically.
So the next question is, how frequently do you experience the Simpsons paradox in your day-to-day job?
I don't mean, it happened. I don't know how frequently. Like it can be different shades, or especially because depends also the type of projects you work on. Like it's mainly when you really have to do some sort of uncrafted or clinical studies. For example, if you work in clinical studies, can be quite important to know this paradox, I say.
Great. Any more questions? You can also raise your hand if you don't want to use Slido. We have some more time left to discuss, so. All right, then. Thanks again for the great talk.
Okay, thank you.
Right, welcome everyone. With us here is Sanskar from London. He's a software engineer at Bloomberg and the creator of awesome open source libraries like Starfire and Robin. And today he's here to tell us all about Robin, which is an async web framework in Python based on a Rust runtime. Welcome, Sanskar.
Thank you for the introduction, Eric. Quick mic check. Am I audible at the end? Okay, perfect. Hi, everyone. Thank you for coming back to my talk. I suppose we all love Robin so much that we speak twice here. Okay, so a quick introduction. In the mornings, I work as a software engineer at Bloomberg, and during the night, I maintain free and open source software, and one of them is Robin. Now, speaking of Robin, we come to the question, what is Robin? Simply put, Robin is a fast async Python web framework with a Rust runtime. But before we dive any further, I'd like to tell you a story, the Robin story. So once upon a time, in the vibrant month of April 2021, there was a diligent university student named Sanskar. He was in the final year of his university and was supposed to submit a final year project. But like all other diligent university students, he spent all his time exploring Reddit. During that time, a major company decided to introduce and incorporate Rust into their projects. And Reddit was filled with memes about rewriting everything in Rust. And I was also working on a Flask project back then, and I had been constantly annoyed by the lack of async support. And scrolling Reddit, I finally got an idea. I asked myself, you know, Sanskar, what would be cool if Flask would have async support? But you know what would be cooler? If it was written in Rust, by the way. And with that epiphany, the idea for Robin was born. But we come to the most important question of the talk, why the name? Now, I thought to myself, if I take care of an entity called Robin, I nurture it and allow it to grow, that automatically makes me Batman. So if I am not responding to your queries for some reason, just have a bat signal beside you, and it's my moral obligation to come to you. Now, since its inception, Robin is hosted on GitHub, is licensed under BSD 2.0 clause, is currently released under version 0.31.0, has more than 2,600 stars on GitHub, more than 750,000 installs on PyPI, but most importantly, it's under active development. And over time, we have acquired some sponsors, and I'm really thankful for them. But most importantly, the project that was started as a single-person project in his room has more than 40 contributors, and I believe that's incredible. But I am absolutely certain that someone in the audience must have had this question. We have so many web frameworks. Why do we need another one? Before I answer this, I'd like to explain the reason myself, and I'd like to explain how I compare the existing frameworks that are available. So for me, the performance is important. Then comes the ease of use, then the scalability, then built-in features, extensibility, hacker or innovator friendliness. This is a term that I've coined myself. I'll explain it further. Then end-to-end app creation timeline, and most importantly, community. Now, if we select any framework in the market, we have to settle for some reason. For example, if the performance is high, then the ease of use suffers. If it is scalable enough, then the extensibility is not there, or if the built-in features are present, it's too opinionated to be extensible. And I believe that we have forgotten about hacker friendliness or innovator friendliness in the frameworks. We talk about collaboration and how it would scale, but it is something that we do not talk about. Community is decent, thanks to you all. Community is actually very nice in most of the frameworks, and end-to-end app creation timeline is decent, but I believe it can be improved. And with Robin, I'm trying to create a framework that excels in all of them. We're not there yet, but we'll get there eventually. So simply put, Robin can be called a fast async Python web framework with a Rust runtime. But a detailed view over it would be a high-performance, community-driven, and an innovator-friendly web framework. Now let's talk about performance. And for it, I will let the metrics do the talking. Robin, according to Tech Empower, can serve over 1 million requests per minute, and we are only getting started. And let us have a look at the architecture to see why it is so much faster than all the other frameworks. For one, we have a Rust core. This is majority of what makes Robin faster than all its competitors. This is a multi-threaded runtime backed by Tokyo. This part allows us to bypass the Python guild and use real Unix threads, so providing us real concurrency. Then we have a worker event cycle that does all the dirty work for us. This part manages the runtime, passes all the instructions to the Rust code. This part also initializes the thread pool and routes all the incoming requests to the thread-safe router. And then when we start the application using the command python app.py, the Python code is converted to Rust objects. Then the multi-threaded router is populated. And then the incoming request hits the router. And depending on the type of request or the type of function that is to be executed, be it synchronous function, asynchronous function, it is dispatched. And finally, the response is sent back to the worker event cycle. So this is the multi-threaded architecture of Robin. Pretty cool, right? Now, imagine it being way faster. So Robin not only supports multi-threads, it also supports multiple workers. So you can have, not only you can use the threads that are available per processor, you can scale it also across the cores that are present in your PC. We have a shared TCP socket that is shared across the processes. So how you would configure that is you just specify the number of processes and the number of workers, and you're pretty much good to go. Now let's talk about the ease of use. I believe that if a framework or a tool is not easy to use, most of us wouldn't bother learning it, because as software engineers, I believe we solve so many hard problems, and if a framework is adding to it rather than subtracting from it, it is not a lot of fun to use that tool. So let us have a look at the traditional Python app lifecycle. Traditionally, we'd have a reverse proxy, something like Nginx or Caddy. Then we'd have a web server like ASGI, WSGI, or potentially RSGI at some point. And then we'd have a web framework like Flask, Django, FastAPI. And let us zoom into the web framework side of things. Quick question to the audience. How many of us know how to write a Flask application? Okay, 90% of the room. So it is precisely for that reason Robin looks like this. I loved writing Flask, and I knew many people loved writing Flask too. I have added some changes and to make the development experience better, but in my opinion, this API is very nice and should be used till people get bored of it. But let us talk about something that was not a no-brainer, that sparked a lot of controversy when I launched Robin, the web server side of things. So here you see a code of the web server gateway interface, or a WSGI. These, a quick history about them, these were created to set a standard. These allowed the framework developers to expose interfaces and the server developers to consume from those interfaces. So the collaboration between the framework developers and the server developers was very nice. The framework developers didn't have to worry about the HTTP execution, and the server developers didn't have to worry about the routing. However, these are pretty nice. Robin doesn't require an SGI or doesn't need one. It comes with a server integrated. So whenever I tell this to anyone else, the usual response is, what about PEP 333? Or what about ASGI? My answer is that if you read the PEP carefully, it was created to make the collaboration between the frameworks and the server easier. But in Robin, the server is coupled, integrated in Robin itself. So you do not need to worry about that. All the dirty parts are handled by us. And this is also one of the reasons why Robin is also faster than all the other frameworks that are available. So if you are deploying a Robin app, you just need to configure a reverse proxy depending on whatever your org is or depending on what your preference is, and then the web server is coupled with Robin. Now let's talk about scalability. I like to split the scalability into two parts. One is how much throughput can the framework handle as the traffic grows. And the second part is how would you structure your code as the project grows. So let's talk about performance at scale. We have already seen Robin is very fast. You can just have a reverse proxy and it will handle over 1 million requests per minute on a regular PC. Let us talk about organization at scale. Robin supports functional views as well as class views are work in progress, but functional views is something that I believe are not available in any other framework at this point. Functional views allow to structure all the codes that are of similar responsibilities under a closure pattern. And I think I usually like to do that, but the fact that I couldn't find it somewhere else was a bit annoying. And if your code base increases and it makes it harder for you to split your code, you can use routers. Routers are a common pattern now. So it is basically like a sub-Robin app that you'd use in a separate file and then include it in the main file. Now, let us talk about the built-in features. I believe that the built-in features should be present in a proper way because they serve as a good solid foundation. And a solid foundation should be important. And also, if there are no nice built-in features, then I'd have to implement everything myself as a user. Then it kills the point of using a framework. So Robin, by default, supports synchronous functions, supports asynchronous functions, directory serving, static file serving, URL routing or path parameters, middlewares, and application events. Okay, now let's talk to the spicy part of the framework, extensibility. It is something that is very close to my heart. I have been a person who has written a custom code editor for myself, so having the freedom to extend the tool is something that's very valuable for me. And for this reason, Robin has a concept called extensions. So we provide first-class support for extensions, as well as the ability to override them, and also you can install them if you want to. It's not shipped by default. So for example, we support templating, and in templating, we support Jinja templates. So you can see, you can just pip install Robin templating and import Jinja templates from there. However, if you do not want to use Jinja templates, we provide interfaces that you can override and consume into your Robin app with the templating engine of your choice. And also, Robin supports GraphQL. So should there be a case where you want to use a GraphQL application internally but have external REST endpoints, you can use Strawberry GraphQL with Robin. So you just declare some types, Strawberry types in Robin, declare a few routes, and you're good to go. Okay, now the built-in features are nice and extensions are also nice, but what makes Robin hacker-friendly? Or what is the term hacker-friendliness? Hacker-friendliness basically means, in my opinion, the ability to create an app quickly. I am a very strong proponent of making web frameworks hacker-friendly because we are talking about how these big applications handle collaboration, how these big applications handle scale. However, we forget that these applications were created by one or two people over a weekend or caffeinating themselves, making MVPs. And the code might have been terrible in retrospect, but it is also a reason why these applications exist today. And for that, Robin supports something called const requests. So what are const requests? Like we talked in the architecture like a few slides back, I noticed that this part of the architecture was very GIL dependent. You had to always acquire the GIL, get the response, and then release the GIL again. However, for simple tasks like JSON payload serving, or file serving, or image serving, or a simple string serving, you do not need to do that. So in Robin, you just calculate the response once, store it in the multi-threaded router, and then the GIL dependence is eliminated completely. So this makes the serving way faster because for every subsequent request, you do not have to acquire and release a GIL. Some people like to call it caching, but there's no TTL. So in Robin, we call it const requests. And finally, WebSockets. Some people may say that it's a built-in tool, but I also use WebSockets in terms of message queues when I'm prototyping a lot of things. So Robin supports WebSockets by default, and you can use it basically like a subrouter. And finally, not needing to choose a server. In the server world, I believe that it introduces a paradox of choice. There's Ubicon, there's Starlet, no, Starlet is a framework, sorry, Gunicorn, and all the other servers that are available. So you do not need to choose any of that. You can just specify the number of workers and the processes, and you're good to go. Now, let's talk about the end-to-end app creation timeline. This term basically means the time required for you to start an application from scratch and get it up and running in the cloud or up and running somewhere. So for that, what you would do in Robin, you'd either install it through pip or you'd install it through Conda. Then we have a feature called Robin CLI. So in my opinion, backend development or web development at this point is not just adding some routes or adding business logic. Now we need to worry about configuring the Docker files, configuring the reverse proxy, and all the other things that allow the collaboration easier. So in Robin CLI, you just type the command Robin create, and it will ask you if you require a Docker image, if the type of web proxy, the type of reverse proxy that you want to use. So it will make the configuration for you, do the boilerplate part for you, and give you a basic hello world route so that you can extend the application yourself. So the part of worrying about the configuration files is eliminated. And finally, if you want to access the docs from the terminal itself without leaving the zone, you can do that. But at this point, it's just an online feature only, but in the future, we'll have docs available in the terminal. And finally, just running in production is as simple as specifying the number of workers and the number of processes. Okay. Now, let's talk about the community side of things. And for that, I will tell you another story, the community story. So the community started like how all the other amazing things start, with a post on Reddit. And then we had a Jitter channel because it was cool to talk with people who enjoyed using the project. Then we decided it wasn't as accessible, so we moved to Discord, which was a platform that everyone preferred. Now everything was nice come November 2022. And for me, in November 2022, life got a bit overwhelming because of my personal events. I was still devoting some time to Robin, but I wasn't as active. However, to my notice, we still made progress. And I tried to see what has happened and how we were making progress because I was approving PRs. And I came to this realization that the community was growing at a steady rate. Many features were recommended by the community, and 60% of the past releases had some sort of community involvement. And the 4 out of the past 10 releases had no involvement from me at all, just a few PR merges. So for that reason, I believe that Robin, being a single person project, doesn't do much justice. It's a community project and should be attributed like that. So Robin will no longer be under my name. It will be under an organization called Sparkles. And this is the logo. And if you want to read more about it, you can go to github.com/sparkles. So yeah, it will not be an individual project anymore. Now let's talk about what lies in the future for Robin. We obviously want to make it more faster, add some automatic documentation generation because it's a feature requested by community a lot, add some sort of runtime data validation, maybe with Pydantic, maybe with MessageSpec, and have auto-const requests, add some sort of ORM support, but still follow the extensibility philosophy, where it's still lean by default, but you can extend the ORM setup. You are basically not tied to the features that we implement. Add authentication and authorization. This will be hopefully done within this week. Improve WebSockets, transition the repos to Sparkle.org without breaking the CIs. Improve the documentation, because I believe that a framework is only as good as the documentation, and the documentation around it should be nice. And for that, I plan to create some video-based tutorials because not everyone likes to read documentation and everyone learns differently. And invest more pragmatic text-based applications. And finally, add more support. And I believe that we are in the year of 2023. Some sort of AI-based support on the documentation website will be nice and help the developers to focus more on shipping features rather than supporting. However, I also still feel that we are serving humans, so human-based support is important. So we will be expanding our community and dedicating some resources for that. So if you are interested for helping us out, join our Discord We hold monthly community calls, and we'll have one next month. And here are some of the important links. It's hosted on GitHub at this point, is on PyPI. This is the website. These are the docs, and this is the Discord. So you can star Robin, and you can ask me any questions that you may have. Thank you so much.
Thanks, Sanskar, for showing us Robin. We have some questions. If you have any more questions, feel free to ask them via Slido or just raise your hand after the first round of questions. I'm happy to take them. The first question is, did you test the performance of Robin against Granian or any other RSGI framework server combination?
Yes. So compared to all the other ASGI, Robin is faster. And for RSGI, it's still under progress, so the performance is changing a lot. So we'll see how that works out. I haven't tested it against Granian, but I think it should be available on Tech Empowered.
All right, and the other question was, I've kind of seen it on the roadmap already, but it's still relevant. Have you ever considered auto-detecting const requests by analyzing the Python AST, or what are your plans for that?
Yes, okay. I think I forgot to mention that. Yes, so we plan to support automatic const requests. Yeah, so this will hopefully be done in the future, but I don't know at what point, but definitely within this year.
All right. Any more questions?
Hi. So nice talk, and it's
Thank
very
you.
interesting. My question, though, is why Prisma instead of SQL Alchemy? I mean, Prisma is, it's open source, but it's from a proprietary company. So just curious.
That's a good question. It's just because I liked using Prisma by default, but we won't be enforcing that and shipping by default. It will be an extension. So we usually also support multiple extensions. So we will support SQL Alchemy as well. But Prisma was something that when I wrote the slides, I really liked using. So that's just one reason.
All right, any more questions? Great, then thanks again, Sanskar.
Cool, thank you so much. Thank you so much.
up here in the front or in the back. Next up, we have Jean-Luc Stevens. He's a software engineer at Anaconda, and he's he's the maintainer of the HoloViews library. And today, he's here to tell us all about HoloViz, a visualization tool. Welcome.
Thank you. Okay. Thank you for the introduction. Is that clear? Yeah, I think that's good. Okay, so here's my talk. It's HoloViz, visualization and interactive dashboards in Python. Okay, so let's get going. As probably everyone here knows, Python has really exploded over the past few years, and it's really being used a lot in, I don't know, machine learning, data science, this kind of thing. There's a lot of people in the world who want to use Python to understand their data, get insights from the data, make decisions based on those insights and so on. And one of the most important tools for actually understanding data is visualization. It's how we intuitively understand things normally with visualization and the way we sort of look at things and we get an intuitive understanding of them. So there's two different ways you can use visualization that I think about. One is to actually gain those insights, and the second one is to actually convey those insights to someone else. So it's a communication kind of role for visualization. So the first step is often what a data scientist is doing. They're trying to explore, they're trying to figure out what they want to do with their data, what the data means. And the second one is sort of when you have an insight and you want to communicate it to maybe your boss or within your organization, you want to make a decision based on something, you actually have to give them the information that you want. And often the way to do that is with a dashboard. You give them a dashboard and they can play around with it. Ideally, it's an interactive dashboard so they can gain the same insight that you had. And that's the whole point of this communication role. So I'm going to show you a sort of example of the sort of dashboard you can actually build with these tools. It's the Glaciers demo, and that should be here. So this is an example of a more advanced app than I'll be talking about for the rest of the talk, but it's to give you an idea of what's possible. So this is a huge number of glaciers, 213,000 glaciers or so, all around the world. You've got a map of them. You have plots of the sort of precipitation, the elevation. You get some histograms. And these plots let you pan, and they're kind of linked. You can pan around with them. You can then do selections on them. And for example, you can select a region here. It takes a few seconds. And then you can see that the histograms update. So you have linked plots, right? And the idea is that you can get sort of ideas about your data that you might not see just looking at it in a sort of tabular format, like a data frame. So here you can see that these are the glaciers. It looks like in Alaska, around here, that have been selected in this little region here. And you can see I have hover information, so I can get the actual numbers for the points I'm on, and I can also hover with the histogram. Okay, so that's the sort of thing I'll be talking about, and that's the sort of thing that I hope at the end of this talk you'll be motivated to build and maybe inspired to try yourself. Okay, so what is HoloViz? Well, really it's a kind of collection of tools. It's a sort of suite of Python visualization libraries. Here they are. And it's kind of following the Unix philosophy. We try and have one goal for each tool. What is this tool trying to solve? What is the problem that this tool is about? And we try to tackle that problem. And then what happens is we hope to try and make those tools work together. So when you have a problem, you often have lots of different aspects to that problem. And no one of these tools normally hits everything. So often you have to combine them together. And actually, that's the way we think of it. Lots of tools that work together. And that's, again, paraphrasing the Unix philosophy. Each program should do one thing well, and the program should work together. So I encourage you to all go to holoviz.org for information. You can find out the sort of idea behind HoloViz here, and you can learn more about it for yourself. Okay, so another important thing in HoloViz is our concept of shortcuts, not dead ends. And the idea then is, if you're an expert in visualization, you might know exactly what to do to build your perfect app, a really polished app, beautiful CSS, really, really good-looking app. But you have lots and lots of decisions to make, and you need a lot of expertise to do this well. So it might take you a while, might be quite a lot of code, but you end up with something that's really nice, you're really happy with it. This is great for someone who's just been given a task of building a dashboard where all the insights have already been made. But if you're a data scientist, you often want to do things like really quickly, iteratively, and you want a high-level tool that just gets you the insights you need, and then you don't worry about the polish, exactly how it looks, whatever. You just iterate, you throw a lot away, and at the end you have the insight, and then you want to polish that. So there are a lot of high-level tools around, and the idea is you pick which direction you want to go in. You say, I want to go in this direction, and you get close enough to what you care about. Like, okay, that's fine. I'm going to do something else now, switch to something else. So you can quickly go far, but you don't always get to that last bit that you want, right? That last bit of polish, that last feature, whatever it is, you don't quite get there. So the goal of HoloViz is we have a layered approach where we kind of do both. You have a high-level tool that takes you pretty close to where you want to be, and then you decide, okay, actually this time I do want to make a nice app. I want to share it with my boss. I want to make a nice dashboard. And that's the case where you go from your high-level tool, you maybe learn a bit more, you need a bit more expertise, and then you do the last bit of effort to do those last few steps where you need to learn something to make that last bit of polish, that last feature, whatever it is that you really need to finish it off and make a nice job. So that's this concept of shortcuts, not dead ends, and that's also quite important. Another important thing is, I'm not really going to show you notebooks, but everything you see does work in Jupyter Notebooks. So actually, a few quick questions. I should have really asked at the beginning, but who here had heard of HoloViz before? Okay, a few. Okay, and who here has used notebooks? Okay, a lot more. That's what I expected to see. Okay, so this is very good for the sort of beginner level talk. So yes, everything you see does work in Notebook when you're exploring, but it also then works for deploying when you have a dashboard and you want to have something that's nice and polished at the end without any code. Okay, so this sort of entry point I'm going to talk about is something called HVplot, and it's our data-centric API. So that means that no matter who you are, you're probably working some sort of data format in Python. It might be a pandas data frame, it might be xarrays, or Dask, GeoPandas, intake, network X, streams. All of these are supported by HVplot. And the reason it's data-centric is that everything comes off a method, a plotting methods, on your data structure. So off your pandas data frame, off your xarray data set, or whatever it is, you can do it that way. So again, I encourage you to go to the docs. You find a lot about it at hvplot.holoviz.org. And I'll give you a quick little example here. So here's a data frame, and it's about penguins. So this is the first 5 entries, or first 5 rows about the penguins. You can see you've got the species of penguin, you have the island where that penguin lives, the length of the bill of the penguin, the depth of the bill, flipper length, body mass, and the sex of the penguin. So this is the data set that I'll talk about. So this is a data frame. Now, if you know nothing about hvplot and you just know about pandas, you might know about the .plot method. So this comes with pandas. It uses matplotlib, and it's quite convenient, for people who just want to have a quick plot with matplotlib. So here, what I've done is I simply did a simple remapping from the species column to different colors, blue, red, and yellow, and then I just used .plot scatter with the native .plot method that comes with pandas to show the bill length against the bill depth, colored by species. So you see these 3 different clusters, right, for the different species, and you also see that some of them have overlap, but that's kind of what you'd expect. Okay, so that's great, but the problem with this is it's a static image, right? This is just a PNG, or it could be an SVG, but whatever it is, it's not interactive. So maybe this is exactly what you want, then you can include it in a publication, you can put it in a scientific paper, you're done, fantastic. But chances are, if you're kind of exploring your data, you're not done. You want to do the next thing and the next thing, and you want to still explore your data and get those insights that you want out of this data set. So for this, the recommendation that we have from the HoloViz group is to use hvplot, which gives you essentially the same kind of API. Small differences, but it's very much inspired by the .plot API and tries to be very similar to it. And the difference now is you can actually get interaction. So now you can hover. You can see the different penguins, the species, the actual numbers, right? So you don't have to read the plot. You can just see the exact number. You can pan around the plot. You can now zoom inside the plot, reset the plot. You can do all these different things. You can even do things like compress one axis or so on and so forth. So there's lots of different things you can do to get some more insight into this data. And that's really great for data exploration, right? When you're not actually finished, you're not going to do a publication just yet, you're still trying to understand what's going on. So yes, hover, zoom, and pan, and I think I showed you all those 3 things. Okay, so this is great, but here we don't have that much data, right? What happens when you have millions or billions of rows of data? Then you might have a different problem, right? If you can imagine this having, millions of data points, you probably end up with a big mess. You just get lots of overplotting, the red points over the blue points over the yellow points, and it's much harder to make sense of what's going on, and it'd just be a big blob, right? So you have problems of overplotting, you have problems of data, because you have to push all this data to the browser, and if you have that much data, your browser's going to get slow, your tab's going to crash, you're going to have trouble, right? So what do you do when you want something easy like this, but you have a big data set? So here's an example. This is a flights data frame, and for my group, this is not a big data set, we don't consider this is what, 918,000 flights or so. That's pretty small, really, but still far too much to really plot effectively. So here's again the first 5 rows of this data. I have a whole load of columns relating to flights, so aeroplane flights, the origin of the flight, the destination of the flight, the distance traveled, the time taken, all this sort of stuff. Okay, now if you put this and just did dot plot with matplotlib, it would probably do it, but it would take a long time. With hrplot, it might crash your browser. It probably wouldn't if you use maybe like WebGL, which we do support, but so it'd probably be on the limit of what you can do, but you wouldn't have a very good experience. So what do we do? Well, as you can see at the top, I've got these little icons. This is the hrplot icon, and this is the data shader icon, and I'll talk about data shader now. So data shading, what is data shading? Well, data shader, the project, is a rasterizer. And what that means is it basically stays on the server, and instead of pushing everything to the client side in the browser tab, it creates an image, which means that no matter how many billions or hundreds of billions of points you have, the most data you want to transfer is maybe the size of your screen, right? As many pixels as you have on your screen, because that's what you're looking at. And with hrplot, if you have data shader installed, all you need to do is data shade equals true, and now you can handle those points. So now you can see I can still zoom and pan and do all these things on all those points interactively without having to worry about the fact that I had so many, hundreds of thousands or millions or even billions of points. It still does it every few seconds, right? So I'll quickly show you the data shader website. So data shader is really, really cool. It makes lots of really pretty things, but it's also scientifically meaningful plots. So here's the census data for the United States, and using special things that data shader offers for large data sets. Here it's got histogram equalization active, which lets you see structure of things without worrying too much about the way you structure your color bar and so on. You go to datashader.org, you learn all about this, all the different specific problems related to large data sets and plotting large data sets, and why you actually really need a special tool that's designed around large data. So here's Manhattan, for example, colorized by the census, gives you, I think, racial types and what kind of people are there, and the information from the census. So you can see Manhattan here, for example. And you can do all sorts of things, mathematical things like attractors and so on. They're really quite pretty. So that's all data shader. And again, this can work with huge, huge numbers of points. Okay. On to the next thing. So now what you've done is you've got your large data set, you've done some plotting in the notebook or whatever, and you've got some insights. You suddenly realize something really important about your data and you want to share it with someone. At this point, maybe you're talking to another data scientist. Okay, just give them the notebook. But it might be your boss, or it might be someone who doesn't want to look at code and just wants to sort of a nice, easy thing to interact with and have the story explained to them. You're telling a story with your data, as the idea, right? And you want to do it without actually using any code. Okay, so what do you do then? So you move to the next tool in the HoloViz ecosystem, which is called Panel. It's a very powerful data exploration and web app framework. It lets you make dashboards in Python that go to the web, so go to the browser, and anyone can sort of visit that URL or whatever. And everything, as I said earlier, works in Jupyter Notebooks. So you can build up a dashboard in a notebook, bit by bit. At the end, you serve it, you get a nice dashboard. You go to panel.holoviz.org for the docs. The docs have been reworked recently because we just had a 1.0 release of Panel. We had a big release. It's been a big effort. It's been a long time coming. But we now have a new release of Panel, which is better than ever before. It's using a new version of Bokeh behind the scenes. And note that Panel is not tied to Bokeh in the sense you can actually use Plotly or Matplotlib and so on. I'll talk about that in a second. So here's a very simple example. You get something called a pane from Panel. It's an image pane. And here's the sort of PyCon Italia snake. You just load the PNG, say the width, you say you want it centered, and that's what it looks like. And again, this would be what it looked like in Notebook as well. Okay, so there's a huge number of things that Panel supports, and I want to show you because there really is quite a lot. So if you go to Panel display types, did not open. Okay, so if I go here, yes, you have a component gallery. You can see there's all sorts of things. You can do audio, you can do bokeh plots, HoloViews plots, which again would work from hrplot, which I showed you earlier, images, JPEGs, PDFs, you name it, 3D stuff like VTK.js, all sorts of things are supported by Panel. So whatever it is you want to visualize, chances are you can actually just view it. For example, data frames, you can just put in a Panel pane, and you'll get a data frame that you can actually display and look at. So there's lots and lots of things in panel which are quite useful. Okay, so that kind of covers what I said here. Also, yes, markup and code. You can display HTML, rendered HTML. You can have a code editor, in fact, which does syntax highlighting with ACE. You can do Markdown. This is, you'll see this Markdown. JSON rendering, all sorts of things are available in panel, right, for display. But panel doesn't just do display of things. It lets you interact with things, particularly with widgets. So these are interactive widgets. Here you can see there's a button. You have a slider, which is a for float slider. You can get selectors, so drop-down menus with tooltips. That's probably a bit too small to see, but there's a tooltip there. Checkboxes and so on and so forth. So you get a whole bunch of widgets. And by combining your widgets with whatever you're displaying, you can make an interactive application. And there's huge numbers of ways you can do this. Again, if you go to the panel website, you can learn about them, how to connect these things together. So, and of course, the other thing to mention is that you can, of course, connect your widgets to your HV plots, which I showed you earlier. So all these tools combine with each other so that you can make a data exploration app with panel that you have, a nice template and so on and so forth. Okay. So here's a small little app example. That's literally all the code. Okay, I didn't put the imports in, but apart from that, it's everything. It's 3 lines of code for a simple little app. You have a function that just returns an image, a panel image, which has parameterized by a number, an integer in this case. It selects a PNG image. You have the slider, which is an integer slider, and then you connect them together. And now you can make a little spinning Python, right? So it's super easy, 3 lines of code, connecting a widget to the thing that you display. So I'm not going to go through the code in detail in this talk. It is a sort of beginner level thing, but I just want you to know that it's actually very easy. And if you go to the docs, you'll figure out how to do this kind of thing yourself, right? I know this is just an image, but again, you can connect with plots, and I'll show you some of those in a second. So now I'll show you some of the more advanced examples. This is like where you might want to go, where you might want to be inspired to achieve. I'll show you some of these apps that we have using a data shader and HVplot and panel and so on and so forth. So I showed you the glaciers one already briefly. I won't go through that one again. But so here's another one, exoplanets. So this is data about all the sort of exoplanets we've discovered over the past few decades. We've found a lot of them. You can see where the Earth is. It's a little icon of the Earth right here. And it's basically showing you where these exoplanets are in relationship to Earth. You can change the way that these points are sized. These are I think it's a certain number of the bigger or more important exoplanets. And you can do things like the discovery year of you can do a range slider showing the discovery year of those exoplanets. There's also stuff like potentially habitable planets, which is none. You can also see which ones could be escaped by chemical rockets, which would be like what we have on Earth. I think it's running. Are these all the ones? An update. Anyway, so you can see that you have a bunch of widgets. You see it is updating. There we go. Might take a second. I think it has to do a bit of computation for that one. Anyway, so you can see that you can do all this stuff. And by the way, the background you see is data shaded, right? And you have hover information. Again, you can zoom and so on and so forth. Okay. Yeah, so you can see it's being updated, right? Based on all this data in the background. And the last one I'll show is ship traffic. Again, I actually have another talk coming about this particular methods used in this thing, but it's really cool. It's GPS transponder pings of ships around the US near Vancouver. You can actually zoom in, and it shows you the tracks of the different types of ship, whether like cargo ships or fishing ships or passenger ships. So again, this is actually a really big data set as well. It takes a little while to load. And if you click, also takes a second or two, you can actually find out exactly which ship. See, this is updated. You can actually get which ship, and if I'm lucky, you even get a picture of the ship. Let's try one more. I'll go actually there. No luck. They don't all have pictures. That's the reason for that. Okay, anyway, so you get the idea. So you can actually do sort of drill down exploration of really large data sets, put it into an app, put it into a dashboard, get some real insight into it. Okay, so that's the idea of HoloViz. We're combining all these tools together, the quick exploration of HVplot, extending it with data shader so you can do the large data sets that you have, And then when you have those insights, put it into a nice panel app and deploy it and show it to someone else. Okay, so how do you deploy? Well, you can actually deploy with just panel serve. It's all based on Bokeh server, but again, you can actually, doesn't mean your plot has to be Bokeh that you're displaying. It can be a plotly plot, a matplotlib plot, a Visu plot. There's all those different plotting types that you support. But you can also serve it from a notebook. So if your notebook has .servable on the right parts, you do panel serve, and you can actually take a notebook that you've developed incrementally and make it into a dashboard. And you see that in a minute. And also, there's some really nice tools such as auto reload. So as you change the source of your file, it can refresh, and you can see the changes that you're making in real time. Okay, so this is some new stuff, which is really exciting. It's WebAssembly. What it means is that we can actually have the code running on the client side. It no longer needs a server, so you can just create a dashboard that is just an HTML page that you don't need to run a server for. Well, you need some sort of server, but not something to run the compute of Python. And what we now have is support for PyIodide and PyScript. These are really kind of new and really exciting things that involve, again, a WebAssembly. There's actually a panel PyIodide gallery where I'll show you some of these. So for example, this one, there's no server here. It's going to install all the code, get Python working in WebAssembly, and there we go. We have now Altair brushing example. You can now do all this stuff, and it's all client-side. It's using the same tools that we had before, just deployed with PyIodide. And there's a whole sort of gallery of all these things. Let's try DeckGL quickly. So it's installing all this stuff. It's running the browser. It's executing the code. And now we have these 3D plots. This is all using panel. So yes, all the components of panel actually have this. We use a PyIodide, in fact, in a different way, which is our actual docs is executable. So if I click run using PyIodide, it says you might have to download something. It actually is executable docs. So this is a swipe component. It's a layout in panel. And now I'm running it. It's executing it. And now I actually have something live, right? Again, no server behind it. It's just the page that is being served. Okay, there's also Jupyter Lite, which is another thing. I don't think I'll show you that, but it's essentially Jupyter in the web browser as a client-side thing. There are limitations with things. When you're trying to combine everything with everything else, it gets tricky, and we have to do a lot of documentation work to make sure it's clear. So for instance, data shader doesn't work in WebAssembly right now. You can't make number work with WebAssembly at this time. There's work being done to try and improve that, and hopefully we'll get that fixed in the future. But at the current time, your large data sets, you probably still need a server for. And you probably want that anyway, to be honest. So as I say here, we do try to document these limitations. So if you go to our websites, you can learn about these things. So yeah, these slides. This is a panel app you've been looking at the whole time. That's how this has been working. It's panel serve. I have had that auto reload. That's how I built the whole presentation. I was working on it, adding stuff, changing the text, watching it update, and I get these slides, right? And it's embedded all these apps, right? So this is an actual mini panel app inside a bigger panel app, which is the presentation and so on and so forth. So this is how this all works. Okay. Okay. Lastly, one part of the Unix philosophy is you choose the tool that you need. So maybe you're a data scientist and you want widgets and you want to interact with your data, but you don't want to make a dashboard. So you might not want to use panel, but you still want the widgets just to explore things. So HVPlot has some other APIs. This is called the interactive API. Again, this is all the code needed for this tiny little app here. If you can see it, I can update the data frame. It's actually the same penguin data set I talked about earlier. The male or female penguins, the bill length, some statistics about those penguins that you selected with a filter on minimum body mass, right? And the way it works is you have your data frame, which is a normal data frame. You call .interactive, it makes it into something called an interactive data frame. And then you get widgets really easily. You can do your pandas operations, your filters, and so on and so forth using the normal pandas syntax. But you actually get a little app that lets you kind of play around with that data. And this lets you do things without needing to have a panel dashboard where you have to import everything from panel and sort of set everything up. But you can, and of course, if you want a nice themed, nice polished dashboard, you probably want to do that. But again, it depends on the use case. If you're a data scientist or who's working and exploring, or a data scientist who's trying to present to someone else, right? Okay, so I'll wrap up now. So for acknowledgements, lots and lots of people have been involved. HoloViz has been around for quite a while now, or at least some of our libraries have been. So here are just some of the contributors. We have many more that were associated with the HoloViews 1.16 release, which was recent, and the Panel 1.0 release. I think every one of the developers of these tools were users first. So it's kind of a classic open source model. It's not a framework, as I said. It's a bunch of contributors, people who start using the tools, want to improve something, make a PR, start using the tools, and then become developers and start contributing. So I would say it's a kind of classic open source philosophy there. Lastly, this month we were announced as having NumFocus sponsorship. So we're now a NumFocus sponsored project for HoloViz. So that's really nice for us. We're very happy about that. Okay, and yes, so if you're interested, we have Discord and Discourse. Both of these things let you talk to us and get involved. If you go to holoviz.org, I think you'll find the information there to get involved. Okay, so yes, any questions?
Thanks a lot, Jean-Luc. We have some questions on Slido. Feel free to keep them coming. The first question is it possible to connect HoloViz to a distributed file system or SQL engines like Impala, Hive, or to pick big data sets, data to display in the dashboards?
Right, so we have, for example, Dask support, so Dask arrays and things like that work. There's IBIS. Actually, there's also, for example, intake support. Intake can connect to things like Iceberg. So there's a lot of different tools, including things that are in the cloud where you don't have the data locally. You can connect to some remote data source and then still plot it and do these kind of things with it. It's actually very important for us because we have a lot of people who use our tools for climate science or geoscience, and often their data is not local. They have to access it through a server. So that is a big use case for us for displaying that kind of data, yeah.
Okay, next question. How is HoloViz extensible with current custom functions, or is it extensible with custom functions, and is it possible to use matplotlib functions, for example?
Right, so there's lots of different ways of using our tools. You have to pick which API you want and for the use case you have. For example, you can have a class-based approach where you write methods, you decorate methods to set up the interactivity and so on and so forth. Yes, we support matplotlib, and yes, you can write a function that returns a matplotlib figure, and you can update that figure and it'll be updated as you interact with the widgets and so on, yeah.
And can you import the panel dashboards to use it with another web framework, for example, Flask or Fast API?
I don't know about Fast API. Maybe someone would correct me on that. But as far as I know, yes, Flask, for example, we had work to make it work with Flask and Django. We've had people wanting to integrate these things with those kind of web frameworks, yeah.
All right. And what's the backend library that HoloViz uses?
What's the
backend library?
Okay, so pretty much everything that Panel uses, which is really now the way we do things in HoloViews and GeoViews and so on, is based on Bokeh. So behind the scenes is Bokeh, but Bokeh is both a plotting library as well as what gives us these widgets and things. So you are using Bokeh in the background, even if you don't want to use Bokeh for plotting. So you might have a plotly plot, a matplotlib plot. You don't need to know that you're using Bokeh. It's just behind the scenes in the back end, as you say, yeah.
All right, and how do you add different tabs to HoloViz?
Oh, there's a tabs layout somewhere. If you go to the docs, I can maybe find it here. Tabs, there you go. So yes, you can have tabs like that.
Great. Are there any more questions? Feel free to raise your hand if you have any additional questions, and I will come bring the microphone to you. Nope, that doesn't seem to be the case. All right, then. Okay. Thanks, Jean-Luc.
Thank you.
All right, next up we have the lunch. Remember, if you want to get a lunchbox, pick up the ticket at the counter if there are some left. The Osteria will be closed today, so it's either the lunchbox or the normal lunch in the main hall. All right.
Okay. Thanks.
Now we have Tommaso with his talk, Code Debugging and Refactoring with OpenBugger, a Python library for self-supervised AI debuggers. Welcome him with a big applause.
Hi, everyone. Thanks a lot for showing up in a sunny Sunday afternoon. I live in Amsterdam, so it's such a miracle that I would try to give the talk from outside. So the idea is that I'm going to give this talk about this package for AI debuggers, in the sense that AI debuggers are supposed to use this package. So there are no AI debuggers ready yet. About me a bit, I work as an AI scientist at HK3 Lab, which is a startup in Trento, Rovereto, about machine learning. I studied in California, neuroscience, but it was mostly neuroscience of GPUs, doing deep learning my whole time. And I've been now for quite a long time in AI before it was a cool thing to do. And I've been recently in the middle of the academia, the academia and startup world, so ending up naturally inside Python and open source development. So the idea is that the last 6 months have been pretty surprising from the AI perspective, mostly due to OpenAI releasing ChatGPT and showing that basically a lot of things that in the community we thought were sci-fi conversations about 2035 are actually our current research project. I, like a lot of other people, got kind of stressed of not having access to the actual neural network and only being able to play with such a system through an pretty bad API. So there has been a huge effort from the open source community on trying to replicate and start building open source research programs to basically get code ChatGPT for everyone, or like GPT-like assistant for everybody in the world. Open Assistant has been one of the first of those projects, and the participation has been overwhelming. I was there from the beginning, met a bunch of friends, and basically what we understood is you need data, you need GPUs. For GPUs, you have to beg venture capitalists and governments, but for the data, there is a lot that can be done, especially because the more a person is specialized and understands something, the better quality data it can generate. And of course, it's not only like writing down data like 1975, but there are a lot of automatic synthetic methods to generate very specific data. So what Open Assistant, like in 6 months, actually 5, is a full-fledged app, is running with compute from Hugging Face, Stability, and Redmond AI. And thanks to also Facebook release of a base open source model, it is actually a kind of decent piece of software at the moment. And it has been no money has been put in and thousands of hours from the open source community into it. Now, how OpenBugger fits into it? It's a small project started in order to generate Python coding datasets for OpenBugger, and then I have some friends that are kind of too good at coding, criticized the initial approach, using regular expression, made me study concrete syntax trees, and then 6 months later, I'm here. There is a kind of almost released package. There is a PyCon branch in the GitHub, which should be fully functioning, except that yesterday night, libcst released their 1.0 version, so I'm not sure that if you pip install things are not going to explode. But basic idea is we want to create a huge data set on how to debug Python code. The idea is that it's much easier to find good code and bug it, and then look back at the original solution, instead of finding bad code that people don't really share. I mean, I produce a lot of it, so I could have just looked into my previous year's pushes to GitHub, probably. But it's very time-consuming to then debug it. And a lot of time to debug code, you have to execute it. And when you start using code written from others, going through execution is a pretty bad idea. So what we do is we use static analysis, and in this case, concrete syntax tree parsing to develop bugs as syntax tree operations. So I might go too deep because I got really passionate about different of these topics. So the spoiler of the talk is that language models really require a lot of data, very specific data. Good data are very expensive, and you kind of have to pay a lawyer price to have it produced. Like if you want a physicist to produce physics data, you need to pay a physicist consultant fee. If you want a Python developer, if you want top-tier consulting, Python consulting grade data, you need to pay 400 euros per hour a top-tier consultant in San Francisco and so on. So the idea is, hopefully, I can persuade you that OpenBugger generates quite good data for very cheap. So just to start, what are language models? And I'm here trying to be very, 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 very basic, not to spend the next 6 months discussing about it. It's a kind of very simple idea that was born right at the beginning of information theory. And it was an idea that was actually very related to digital communication and phone. And it was a tentative, actually, an early tentative of information theorists to compress data before communication. And then turns out Fourier transform is much better and so on. But the idea is that you are defining language as a sequence of tokens. A token could be a letter or a phoneme or a full word. And you only care about the sequence of letters or tokens in terms of their autoregressive ability. That is, the possibility of predicting xt plus 1 from the x that were coming before. In the case of language, let's say the tokens are, assuming the tokens are word, typically there are smaller components. Like if I say the sentence, the cat is on the, if people were born in Italy, we had the cat is on the table as example for every single English class of our life. So it's very natural to autocomplete in that direction. And that's kind of how the model does, only that instead of seeing our very subjective sequence of tokens that each of us experience through life, this is trained over the whole internet, or all of the internet that you can scrape without getting sued after you train on it. And what is the problem of these language models? These language models are literally tables where you have one side that is all the possible permutation of sequences up to that length, and on the other side you have all the possible tokens. So you can think that if you have only 2 tokens, you have, 4 possible sequences. But as soon as you have 3 and so on, you start having a huge amount of combinations. And these combinations are very conflictual with machine learning approaches. That is, the longer the context, so the longer the sentence, the more sparse the data are going to be. And the more data you're going to need to actually get a good estimate. So if you want to learn probabilistic models of 2 letters, it's going to be exponentially less data needed than 3 letters, 4 letters, and so on. And this was basically what killed this approach and made it a small subsection of an MIT department for 40 years, till we moved into neural networks and large language model. So the idea here is that even if the space is huge, actually kind of infinite from a human uncountable from a human perspective, like there are more possible combination of 8,000 tokens than there are atoms on the planet. But turns out that both humans and large language model are able to estimate the manifold of plausible token sequences that are still language in a very efficient way. So why these large language models are working now? They're working, we have this sort of ability to train this sort of function approximators since the early 90s, but it was very inefficient, and the way that older models were trained was sequentially, like as if it was a for loop. And because it was a for loop, it was very, very difficult to parallelize. And because it was very difficult to parallelize, it was very inefficient to scale as a computation. 2017, Vasvani, a senior at my PhD, during internship at Google, they developed Transformer, most cited paper that is going to be probably of the century very soon. And basically, they have an architecture that we had for 20 years that now can scale to 3 trillion of tokens. And indeed, that is what happened. So what did OpenAI did? Why did OpenAI, why, even if it was a Google invention, why is ChatGPT a model from OpenAI? Because they really believed in that result. Because they were a company whose fundamental was building a very efficient cluster to train big models. And once they found that architecture, it was the biggest breakthrough possible from there, because all of their compute could be allocated to training. Google has a very complicated budget for their computing and so on. OpenAI had $500 million from Microsoft to only spend in parallelizing transformers. On the other side, they had a very big experience on reinforcement learning from the Dota video game playing agent that maybe somebody remembers, and from a lot of stuff on robotics that are kind of disappeared, but they had a very dexterous, skilled robot. And they were expert, they had state-of-the-art code, and it combined the two things. And ChatGPT was out. This is the famous slide describing the pipeline that they have on their blog post, which kind of separates in 3 steps the creation of a chatbot assistant. The first step is large language model pre-training, which is kind of the most expensive and fundamental step. And this was the breakthrough enabled by transformers. And you literally need to take billions of sequences, actually hundreds of billions of sequences, ending up being at least 1 trillion, 1.5 trillion of tokens seems to be the correct number at the moment. And here is where we think that the model actually learns things. So most of the knowledge is learned in this step. And here knowledge means mapping from sequences to sequences, that sometimes in language, mapping from a sequence to a sequence is just a simple continuation, but other types could be a very complicated operator. You could be saying input, apply mathematical operator, output. Now this operation is a very complicated operation. But if there are enough examples, this model are learning them. Then there is a second part that is actually what OpenBagger is hopefully contributing into, which is creating instruction tuning data set. So it's not only plain sequences of text, but this is your command, this is your input, this is the output that you're supposed to be done. And this is like the very expensive to produce part, because if you want to have very good demonstration, you need to pay people that are very good at that. And that is what OpenAI did in comparison with cheaper work, in synergy with cheaper work that they got from Scale.ai. There were a bunch of scandals of remote African workers labeling for OpenAI. And basically, they used the workers to give a feedback to the model and then train it with reinforcement learning that, as I was saying, they developed a lot of infrastructure for Dota. They use it to finally fine-tune the model. The first part gives the model knowledge. The second part gives the model the ability to follow instruction. The third part gives the model that human feeling during the conversation. Most of the open source models do not have the third step. So again, OpenBagger is coming in the middle, in the second step, and the idea is that we use Python syntax tree mutation to generate high-quality debugging instruction. And that's where we go. Going back a bit to the first part, and I kind of want to give an update of what happened over the last 6 months in the language model department over here. So the idea is that there was the animal farm to the rescue. Facebook released the Llama model, which is a GPT-style pre-trained model. The model was trained on public data, but the data were not released. So the weights were public, but they required a form to be accessible. But then in 2 days, somebody committed a torrent link to the, to the repo, and the commit is still there. I think it's going to be one of the best memes of this phase of AI. And yeah, so basically now it's based Llama for everybody. And right after that, Stanford did another kind of epic thing from my perspective, where they just trained Llama on ChatGPT outputs, ignoring that last big line of the TOS from OpenAI saying that you cannot do it. And turns out that OpenAI did not sue Stanford, so we all can do it now. Month later, the same guys actually from Alpaca from Alpaca, released an open source replication of the dataset from Llama. And this opened up dozens of different companies producing alternative models. Okay. So the idea is that the base LLMs are getting sold mostly from competitor companies trying to enter the space, and they have no private. They cannot sell a competitor to ChatGPT, so they give it for free. And that's kind of nice for us. And so what about the instruction tuning part? The instruction tuning part, there are thousands of groups doing the same thing I'm doing and creating data about their specialty, basically. So back to OpenBagger. So the idea, again, just to repeat, given that I went through 6 months of super fast time in the meantime, we try to use good code to generate debugging instruction instead of bugged code to generate it. The idea is that faster to implement a finite number of transformation that takes good code and move it into bugged space instead of the opposite and learning every possible mapping from bugged to not bugged. We use libcst, so the bugs are introduced not as a string operation, so it's not a regular expression matching something and changing the string, but is a graphical operation over the tree. So there are some nodes we take the source code, represent it as a directly acyclic graph or as a hierarchical tree, and then substitute some of the nodes. Because not all the operations are actually possible in this way, so at the moment we only restrict to a single node substitution operation, such that we can always invert the bug. So we can chain bugs and invert them, and we are always able to go from good code to bugged code, back to good code again. So what are concrete syntax tree, and what is libcst, which is the package that allows us to run it? And basically, concrete syntax tree are a complication of abstract syntax trees that maintain all of the side information. So abstract syntax tree is a decomposition of a string representing source code that only contains nodes, operation, and the value of those operations. While concrete syntax tree, like in this way, concrete syntax tree also contains spaces, comments, and new lines, which means that there is a one-to-one mapping from concrete syntax tree to string, while there are multiple abstract syntax trees that could correspond to the same string of code. Because of this can be used for code generation, and that's what Black or other linting packages use. We are using libcst, which is the Instagram, so Facebook, open source library, and it is kind of the state of the art for code generation. So how do debugging works? The idea is that libcst has a structural match over a subset of the code. The code is modified by a node substitution. The new graph is inverted to generate some code. And this is the debugged code. The debugged code then can be parsed again. The nodes can be substituted again for debugging. These are the bugs that we currently have implemented. There are also some NumPy and the Pandas package-specific bugs. It's nothing fantastic. It's more an example, but they look kind of okay at the end. So this is like an example. So this is an infinite while. This is a bug that nobody here should be producing by themselves. But basically search for all the while nodes and substitute the target condition of the while nodes with a true. So the loop is going to go forever. And there's also is a bug that you cannot solve by running the code. So it was a bit to show off the power of static tools. So this is the example. This is the original condition. And that is what would happen after the bug application. This is the debugging stack trace that we automatically generate from inverting the bug. And this is kind of the big contribution that we have to data generation, is that we're able to generate these automatic, very precise and correct by definition debugging traces that then we will feed to GPT to create fake conversations about debugging code. This is another example. So this is a bit more complicated. So it's like, this is actually something that can happen. So in Python, one keeps going back and forth in between lists, sets, and dictionaries, and they all have a different concatenation method. And this is searching for your dictionary and putting an append instead of a concatenation, or going to sets and adding updates and things like that. So Again, many more steps. There is a cycle of recursive structural matches, and then the code substitution. This is the example. We have a list, and we make it a dictionary. Now, this is what do we end up doing? How do we use it? We take 2,000 lead code examples. So this is a competition, about coding competition. The input data are correct, exercise objective, good code, and what is the optimal code to do it? We apply libcst to parse all the code. We find some code that was, as a part of the solution of the competition, that is not even syntactical, and actually some JavaScript code in the middle. We remove that. We parse it with OpenBagger, inject bugs, and create 20,000 couples of bug and debugged code, and actually debugging trace. We give this as input to GPT, and use it to create 20,000 example of debugging operation. So this was the code that actually has some simple bugs that change the names of things. And this is what GPT comes up from the bugged code and the original code as a beginner question. And this is the answer that, as you can see, is using the debugging trace from that I showed before to as a input, as a grounding data for the generation of the answer. So GPT does not have the possibility to come up by itself with a coding solution. It already has the solution, so it's only giving natural language translation of the code that is already there. So we do not have to hope that GPT creates good data. We have by default data. Of course, sometimes it still makes it up, so we parse the output and check that the syntax tree of the output code is actually the syntax tree of the code that we generated. So just to go back, hopefully I'm kind of proud that I made it on time. The language model requires a lot of data. Good data is difficult to generate. We all would pay not to stay there and reply to someone else how to do those things. So that's what we did a bunch of years ago in the Stack Overflow era. And hopefully I can persuade you that this is a good idea to generate bugs. The bigger limit of this approach is, of course, is that you need to come up with the bugs and implement them. And I'm very good because that's what I do 99% of the time while I code, but there are some people that maybe here are too good to come up with that writing code to come up with, to realize how normal persons may bug the code. So just to finish, HK3 Lab, we are a research lab in Rovereto. We're actually fully remote. We are funded for a bunch of years from Horizon 2020, and we are hiring on metabolic time series forecasting and gigapixel computer vision. That is computer vision over gigabyte-sized images that, of course, have a lot of compute problems. Other hat, new open source community about AI and machine learning, kind of a lot in the meme direction, and that I'm coming up with. The website is not really up. The GitHub is up with a lot of private code full of OpenAI keys forgotten into there. And if you guys are interested, please contact me. If you are searching for some machine learning project, we require skills at every level of the Python stack. We have 3 big projects. One is Baby Dragon, which is a chatbot, long-term memory and chatbot vector index package, something similar to LangChain, but more on the scientific stack. We have InfiniPy, which is Pygame engine, which can be played by GPT. So GPT reads the source code and acts, and actually GPT can write actions as code. So the idea is that it's a video game where everything can happen because you can modify the source code of the video game through happening. We only have demos, but if you are interested in this, come please help. And then, so finally, the latest project, which is kind of crazy, we are starting to digitalize all of the Akkadian and Sumerian tablets that we can find, because it turns out that GPT can translate a bit of Sumerian, so we want to actually train it on that. And yeah, this is a demo of what Baby Dragon does, which is like a chatbot package that has access to your Vent environment and automatically use libcst to parse all of the all of your code base, and then you can use it to ask questions. So anything that is in your computer can be indexed and used to search. Now it uses GPT as a backend, but it can also use open source language models. And I'm done.
Thank you very much for the talk. There's a question on Slido. Is the aim of the model always to correct the buggy code, or also just to spot the bug? If so, how do you ensure that the correct code is feasible to infer?
Okay, so the second part is easy to reply, the first one not. So for this project, yes, the objective is creating a debugging sets, but it's actually one could use the same sort of approach not for debugging. As an example, I could minify the code through syntax tree operation, which is kind of simple here because it means removing all of the new lines and all of the stuff. And then I could have a task which is not about code debugging, but about code minification. Instead, how do I know that the code can be debugged? Because we start from debugged code. We start from working code, invert it, and only use bugs that we know we can invert. So if there are a lot of exceptions for the syntax tree operation, like sometimes you put a new node and you end up removing something, or like inverting it, you get a very anisomorph tree that is not exactly the same. We discard those situations. Thankfully, like we are in a situation where we can generate much more data than we are actually able to analyze. So we can be a bit have some false positive and then analyze, remove the false positive, and only be sure to use things that we can invert and we have full control into.
Okay, thank you. Do we have any other question in the room? Because we have some time. So if you want. No.
Just a comment, so the same approach could be also used for the language identification in generally.
For, you mean
yeah, so
like programming language or human language?
Also programming languages and probably also the spoken languages too.
Yeah, so the idea here actually comes from some ideas on using this translation approach. Like it actually comes from English to German translation and so on. So it's like a lot of time people in translation or like people that work in natural language exploit translation. So they translate something and then they do some operation after translating it, then they map it back and they want to check that the operation is consistent. And this typically you only have data in one language, so you can, and this also happens for styles transfer in image generation with cycle GANs, where you have two data sets and you want to have a model that maps from one to the other, but also invert it back. And here I realized that I was guaranteed to be able to invert back, so I kind of went in that direction.
So theoretically, from one language we can translate to another one, like from a Python to...
Okay, I have a collaborator that helps me, that helped me on this project. My biggest social challenge was stopping him from trying to translate Python to Rust like this. And I've seen that already, some people twitching. Yes, but it is difficult. Like, I think it would be more like from some specific operation. You want to do like, I take all the for loops and it's a bit of, this, it requires really knowing the language to do it. It's above my pay level.
Hi, nice talk. Thank you. First question is, when is this going to be released?
I have to sleep, remove the OpenAI keys from it,
Okay.
and check that there were no, and I have to check whether under the PIP package, do you know if it is open again? Like they closed the registration to PIP a few days ago.
Huh, okay.
So maybe I will release it on the test PIP. I mean, I will open this, I open source the code in a few days, but I'm not sure I can do the pip install because I didn't have, I tried the other day to register and it was blocked for some attack.
And the second question is there a size limit to how much code you can put into this?
Yes. So the size limit is like the wrong question at 2 seconds from the end because I can really go for 6 months into it. So that's the biggest limit. And I think also the biggest
opportunity for good mathematical thinking in language models. That is this information bottleneck. We only have access to a limited prompt, and we have to decide what to put in it. Actually, that's why the minification part, because as I was saying, we have some problem with pandas that has 14,000 tokens classes, and we can't embed them and use and search on it. But yeah, there is a limit, and the limit is 1 page, and 150 lines of code, 200 lines of code. More than that, I wouldn't trust it.
Thank you very much for the talk.
of this conference, please forgive me. It was literally prepared overnight. So it will
Now we have Emanuele with this talk, Serverless Computing for Mathematical Optimization. Welcome in.
Thank you.
You can ask question on Slido, so please, and the stage is yours.
Thank you. So we all know Python as the language for data science, machine learning, and artificial intelligence. However, Python is also an optimal tool to solve optimization problems. Today, in the next 20 minutes, we will try to understand which tools Python can provide us with to solve mathematical optimization problems and how serverless infrastructure can help us making our solutions more efficient and by staying cost effective. But before doing that, we need to set the stage for a very complex and important problem. We will go back in the past, far in the space. Let's go to California in 2018. In 2018, California was the first state of the United States to commit to 100% renewable generation by 2045. It was a bold move from the Democratic governor of the state, one in stark contrast with the US President, Donald J. Trump. Still, California, up until 2018, was a shining example in energy transition. From 2009 to 2018, it has raised its share of renewable generation from less than 4% to about 25%, mainly thanks to the rise in wind and solar production. However, when in 2018 the new energy policy was announced, not everyone was smiling. And I'm not referring just to Trump supporters, I'm also talking about brilliant and rational engineers at CAISO. CAISO is the California Independent Transmission System Operator, the organization in charge of managing the high voltage transmission line in the Golden State. Think Terna in Italy, it's exactly the same thing. Since 2012, CAISO was warning about the so-called duck curve. In the future, they were saying, solar generation will be so predominant that in the middle of the day we will have too much generation, and in the evening we will have too much demand and not enough generation to meet it. You see this curve? It goes worse and worse from 2012 to 2020. This chart is from a report published in 2013, so 5 years before the energy policies that I'm talking about, and it has forecasts up to 2020. So there is a real problem here, and you would think that this problem being known since 5 years before, they would have done something to solve it. No, they didn't. They didn't, and the consequences are here. In 2019, 4% of the total solar generation in California was curtailed. That means wasted. That's enough energy to power a city like Florence for a whole year. This energy was clean energy, zero-cost energy, wasted because there was not enough transmission lines to transfer it to other states in the US. So within the same country. Good. This issue brings us to our problem. We need to model power systems and power markets, but we need to model future power systems and power markets because we need to take now strategic decisions that will result in good or bad consequences in years, if not decades. So when we have to face problems like this, engineers have to make models. For one of our customers, we created a system that is capable to create scenarios for the European power market up to 50 years in the future. In doing that, we faced an interesting problem. That is, how we solve the duck curve. Well, the solution is already known. We need some kind of storage to drain power from the grid during daylight, daytime, and release power into the network during nighttime. This technology nowadays is lithium-ion batteries. It can be a different technology in the future. The point is that we are not sure how these plants will work into the power systems. This is an idea of how utility-scale battery packs will look like, and that's a rendering from General Electric because there are a handful of plants like that in the whole world. There are a couple in Australia, 3 or 4 in the United States. There is some experimental plant in Europe, but that's basically it. So we need to model something that does not really exist yet. How can we do that? The answer is, let's resort to mathematical optimization. We can assume that the actor in charge of operating the battery packs will try to maximize its economic profit by complying with the technical limitations of the batteries themselves, because you don't want to burn down something that is worth tens of millions of dollars, of course. Now, welcome to Mathematical Optimization 101. I will try to squeeze a very complex topic in 2 minutes, and bear with me. In mathematical optimization, we have 2 great families of problems. We have convex problems, and we have non-convex problems. So I'll get in a minute to explain what a convex problem is, but the point is that as long as we stay in the convex problem family, we have a complete mathematical discussion about that. We know how they work, we know how to solve them, we have very effective and efficient algorithms to solve optimization problems with thousands of, even tens of thousands of variables. If we go into non-convex problems, we are in troubles. They're very hard to solve, and as of now, we have no general purpose algorithm that can give us guarantees about the solution. We know how to solve efficiently a couple of families of non-convex problems, but they're very niche cases, like computing the PCA of a matrix. We know that the solution is the eigenvectors of the matrix, but we do not have general algorithms. So now, when is a problem convex? From now on, I will talk just about minimization problems, because a maximization problem can be framed into minimization 1. If you want to get the minimum point. If you want to get the maximum point of f of x, you can just look for the minimum point of minus f of x. So we will talk only about minimization. A problem is convex if you are minimizing a convex function on a convex feasible set. So you have to show that the function is convex and the set of the feasible set is convex as well. For the set, it's usually easy, because if you limit yourself to linear inequalities and to greater than or smaller than constraints, then you're guaranteed that the feasible set is convex. The difficult part is the function. A function is convex if first, a set is convex if you can join any 2 points with a line without going out of the set itself. That's the definition of convexity for a set. A function is convex if the area of the space where it is defined over the surface defined by the function is a convex set. In other words, you should take any 2 points on the surface described by the function, and you should be able to join them with a straight line without going below the surface defined by the function. Okay? Okay. Which of these 2 functions is convex? Right or left? Good. That was easy. However, how many optimization variables do we have in our problem about batteries? So again, we want to optimize the economic profit of the actor operating the batteries, respecting the technical limitation of the devices for 50 years in the future for tens of different types of batteries. So even without taking into account the different types of batteries, we have like 400,000 optimization variables. Multiply that by 50 kind of batteries, you go into the 20 million kind of variables. Good luck trying to chart a function like that. It's impossible. I mean, we cannot draw anything above 3 dimensions. We are going to 20 millions. So no. How can you check if a 20 million dimensional function is convex? The good answer is you can't. You can try with sampling and checking the definition, but that's a huge space. You are never going to cover it in even a small portion. You can try and show that it is convex by hand. Good luck again. However, the guys at Stanford came up with this very interesting idea of discipline convex programming. That is, you should not check if a function is convex. You should build the function so that you know that it is convex. We have some mathematical rules to build function and preserve convexity. For example, the easiest one is that we know that if we sum 2 convex functions, we are going to get another convex function. There are many such rules. Some of them are as easy as the one I just presented you. Some are more complex, but they can be automated. So if you draw your function from a specific set, and if you follow just basic operations such that sum, multiplication, division, subtraction, function composition, which is basically everything you want to do, then you can check immediately if a function is convex or not. How can we do that in Python? Well, we can use a package called CVXPy. CVXPy is great. I mean, it simplifies a lot the way you define convex optimization problems. It gives you a set of functions that you can use, and it gives you a lot of operations that you can perform with such functions. Here is an example from their documentation. The idea is that you have a matrix A, a vector of optimization variables x, and a vector of constant parameters b. And then you use the sum of square function, which you are guaranteed giving a convex result. Because squares are convex. If you sum a number of convex functions, you preserve convexity. So you know that the objective function at line 10 is convex. No matter what is in A matrix and in the B vector. It doesn't matter. It's convex. Great. So now we know how to build our optimization problem. If we solve it, oh, by the way, another great stuff that CVXPy does is it translates this formulation into matrices then get passed to the low-level solver. So you don't have to build the matrices yourself. You just define the function with the discipline convex programming paradigm, and then you let CVXPy do the job. That's great. Very good. We now know how to define our problem. Imagine that here the problem is not something like a constrained linear regression, but it's something like a, let's say, a maximization of economic profit subject to technical limitation of batteries. The solution is something like this. The colors are different kind of batteries. This is 24 hours within the day. And you see that the battery is releasing energy, so it has a positive exchange with the network during nighttime and during evening, and it's drawing energy from the network, so it's charging itself during daylight, because it's basically flattening the dark curve and taking the excess energy produced by photovoltaic plants. That's great. But here comes our iguana, and the point is, okay, good. You know theoretically how to write and to solve the problem. Now the point is, have fun doing that. Still, you have 20 million variables, and even if it's a convex problem, it's still 20 million variables. Imagine just creating a 20 million by 20 million matrix of floating point values. Tough luck. The first time I tried, NumPy told me, Lele, you're trying to allocate memory for 2 terabytes. Do you really believe you can do that? No, you can't. Of course you can't. You must be smart. And the way of being smart here is using sparse matrices. So the matrices in our optimization problem are mainly made of zeros. And zeros can just be neglected. We can just save the information about where the non-zero elements are and what is their value. This saves us a lot of memory. And this makes also the solution of the problem much more efficient. Is it enough? No, absolutely no. We must be smarter. The point is, you have to solve the problem for the next 50 years, but is every day dependent on the previous one? Theoretically, yes, because you preserve the state of charge, but these type of storages are meant to work in a daily cycle. So they charge during daylight, they discharge during the night. They're not meant to preserve energy long time. Also because lithium-ion batteries do not work in the long run. You need other type of technologies that we do not have right now. We can use, pumped hydro in the Alps, but it's difficult. So we can divide and conquer. We can say, why should we optimize for 50 years? We can optimize for every month, or for every week, or for every day. Empirically, we understood that the best way to do it is to optimize for each month. So you don't have a huge optimization problem. You have 50 times 12, so 600 smaller optimization problems. Then you have, of course, to force boundary conditions to preserve the energy conservation principle. You can say that the batteries are halfway empty at the beginning of the month and halfway empty at the end of the month. It's reasonable. It's a simplification, sure, but it's not very different from how the real world would look like. Great. Now we have 600 small optimization problems that we can solve independently from one another. Why shouldn't we run everything in parallel? Because we don't have 600 cores on a machine. But we can spawn 600 Lambda functions. Why not? They can run in parallel. And here is where the serverless computing comes into play. What we do is to have a cloud composer, which is basically the Airflow that you pay a lot on Google Cloud Platform, orchestrating a pipeline. At some point of the pipeline, it writes some input data on a bucket. When each file is written on the bucket, a cloud function is spawned. So we have 600 files, 600 cloud function, one for each optimization problem. And each function solves an instance of the optimization problem for a single month. Then it writes the results again in another bucket. The orchestrator is pulling the bucket. When it has 600 files, it merges all the results, and it goes forward. How long does it take? Well, 5 minutes. With the serverless solution, we basically skewed the time that it takes to run the whole optimization on 50 years to the time that it takes to run the optimization on a single month. Because GCP will give us the infrastructure and the elasticity to scale up to 600 parallel executions. So the question is really, how long does it take to solve one optimization problem and to start, and for the cold start of the cloud function to kick in? It's 5 minutes. Good. And that's it. That's how you solve complex mathematical optimization problems with the help of CVXPy, some mathematical knowledge that you have to get, and serverless computing. I am Emanuele Fabiani. I'm head of AI at Extreme, where we solve business problems with artificial intelligence.
Some questions will start appearing on the slide. The first one is, why serverless? Any consideration on cost vs using spot instances?
Any considerations of it?
Spot instances.
Oh, spot instances. Just because it was easier to code this stuff on cloud functions. I mean, the idea is to have a lot of computing power for a very short amount of time. And cloud functions are great because they spawn very quickly and they cost very little. I mean, a full run of the full optimization problem on 50 years, it costs like €3. So very affordable.
That was the only on Slido. There's someone else in the room directly that want to, yeah.
Like mathematically, what's the kind of optimization problem when you write down all the constraints? What type of optimization problems was it that you applied in this specific case?
So the real problem would be non-convex. So we designed a convex relaxation which translates ultimately into a quadratic optimization problem. Constraint quadratic. Yeah.
We have another question on Slido before. How much did it cost to run 600 function?
€3.
Free? Oh.
€3, yeah.
There's already an answer.
Outside the free tier, that is.
Yeah, great talk. Can you elaborate a bit more on Orchestrator in case of the Google Cloud? Is it like you configure it in the UI, or is it the code that you can reuse for another optimization problems?
Oh, cool. So you asked the orchestrator, right? Yeah. Okay. The orchestrator here is Cloud Composer, which is a hosted version of Airflow. So it's basically Apache Airflow, and we wrote all the code for the scenario generation as Airflow tasks. So Airflow is managing everything, and then when it needs to call the functions, it goes to write files in a bucket. So the cloud function is basically just a main. Of course, it's the function with the usual GCP format, but it's like a main where we use the modules that could be used everywhere else. So the module that solves the optimization is completely abstract. Then it's just, let's say, used inside the script in the cloud function. So it's completely reusable.
Thank you for the presentation. My question is more related to the low level of the processing.
Mm-hmm.
I'm involved in very heavy computational processing. And in the past, before the cloud era, I'm thinking about 10 years ago, we decided to develop most of the stuff in C code, okay? For what you have seen in this specific case, Python code is now ready compared to Rust or C code or matter of application to do very heavy computational in reasonable time and reasonable cost, or the solution to move to C code and Rust is still a good solution, I mean, or a good strategy?
Okay, great question. The answer is no, it's not. The computation is performed in C. The idea is that CVXPy uses low-level primitives that are written in C. So the idea is that you use Python as a, sorry, maybe he has, okay. You use Python as a developer-friendly interface, but then the heavy lifting is performed in C.
Yeah, exactly what we did. So thank you for this. And just because we talk a lot about Rust during this conference, and I was very surprised, and even it's a pleasure because I'm very interested in. What is your opinion in the comparison C and Rust? If you have the way to do so, to answer.
Okay, so for this specific use case, I'm not sure if Rust will ever catch up with C code. Why? Because we know how to solve efficiently convex optimization problems we have been knowing it for many years now. And we already have some very good C libraries in C made by very good researchers, and it would take a lot of effort from very specific people to rewrite everything in Rust. And I'm not even talking about the risk of messing up with bugs and so on. So I don't see how this will happen. What I see is that from a certain point on, which I'm not sure how far it is, people will start using Rust to write high-performance code. So the idea is that the newest packages will be probably written in Rust, but there is so much legacy code here that there is no way they are going to rewrite everything. It's not economically feasible.
We have another question on Slido that is, how sparse was the matrix?
I mean, very, very, very sparse. So it's like 99.9990 zeros. It's mainly the main diagonal and few other spots because the matrices were built from let's say, they were built from automatic translation of functions like this, and they were just made to compose other pieces. So the big square matrices were almost completely sparse. So the gain in memory footprint was huge.
We still have 5 minutes if you want to ask other questions. Okay, we have other two, one moment. So, did you consider other approaches to decompose the large problem? For example, with ADMM?
No. ADMM is great. I've used it during my PhD. But if you don't have to use it, maybe it's better not to use it. Because, I mean, if you can frame everything as a quadratic problem, why should you go for ADMM or other advanced topics? I mean, it's the simplest solution and it does the job. So I would say that it could have been possible to use ADMM, but it was not probably the simplest solution. So we opted for this one.
Right. The other one is, any considerations using an OSS solver like CVXPy over commercial software like Gurobi? Are you using majorly OSS solvers in productions?
Let's say they're not the same thing. So CVXPy can be used with Gurobi for the low-level optimization. So CVXPy can allow you to write the problem in discipline convex programming and then translate everything into matrices that then get pushed down to Gurobi or your favorite solver. What we did was to take the best, let's say, 5 open source solvers and benchmark them. I can't remember which one we chose, but it's completely free. It's open source. Maybe I will add it at the end of the slides. And we didn't even try Gorobi because, I mean, why should we pay for commercial software when the gain is basically non-existent because 5 minutes are already more than enough for our use case. I must say that I did use Gorobi for my PhD when I had to solve a pretty annoying non-convex optimization problem with, let's say, alternate coordinate descent. And there, Gorobi was superior to anything open source I could find. But it was a very specific use case. I mean, if you stay into the realm of quadratic programming, I mean, the algorithms are well known, so you don't have to go for something commercial that may be better, but just marginally better.
We have room for maybe 1 or 2 questions. Someone? No, okay. Thank you very much.
Thank you. I mean, again, sorry for the improvised talk. I hope you enjoyed it anyway.
scraping o UI automation, con la sua talk Scraping o UI automation da livello scimmia a pro.
Buon pomeriggio, oggi appunto come avete sentito parliamo proprio di questo, sono Nicola Landro, qui potete trovare le slide e tutto il materiale che userò in questo talk, sono Head of Engineering in Digitiamo e Liotech. Quindi di cosa parliamo oggi esattamente? Di UI Automation vs Scraping, inizieremo così, poi parleremo di tool prefabbricati, faremo una piccola parte in cui guardiamo le varie fasi, le librerie HTML only, le librerie basate su web browser, i tool di UI automation e poi un piccolo introduzione sul testing e le librerie di testing. Iniziamo subito facendo una piccola comparison tra UI automation vs scraping. Che cosa si intende per UI automation? Alla fine si intende tutto quel software che simula il mouse e la tastiera alla fin dei conti, per poter simulare la presenza di una persona sul PC. Quindi il topic principale è simulare l'umano con lo scopo di test tipicamente. Al contrario, il web scraping ha sempre l'intento di simulare l'umano, in particolare dentro un browser, e soprattutto tipicamente il web scraping non è a scopo di test, ma a scopo di ottenere dei dati. E un piccolo, anche per distinguerlo, lo scraping dal crawler è semplicemente che lo scraping ha un obiettivo specifico, un sito, voglio estrarre questa informazione e quindi il mio scraper scrapa quel sito ottenendo quell'informazione. Al contrario, il web crawler ha un obiettivo ben più ampio, ha una serie di link, ne deve cercare altri, deve vagare nel web fino a trovare il dato di interesse, quindi molto più random, molto più di ricerca più casuale. Tool prefabbricati. Il primo modo per fare uno scraping, il più semplice, è utilizzare un tool già pronto, con un'interfaccia grafica. Per esempio WebScraper.io, per esempio Bardeen, che oltre a fare lo scraping ha anche una serie di pipeline possibili da mettere in successione, piuttosto che anche applicazioni desktop come Impert.io e molti altri. In particolare noi vedremo WebScraper.io al volo, semplicemente è un plugin che si può installare nel browser, con F12, il classico comando con cui accediamo ai tool per sviluppatore, troveremo una voce nuova, Web Scraper, in cui possiamo incollare il nostro sito di partenza per lo scraping, avremo a disposizione dei vari selettori. Possiamo selezionare il tipo di selettore di interesse, testo piuttosto che elemento, e una volta selezionato avremo un bottone per poter cliccare la UI e tirerà fuori lui la query per ottenere l'oggetto o gli oggetti di interesse. Quindi molto, molto grafico, ancora abbastanza dev perché comunque si trova nei tool per sviluppatore. Una volta impostata tutta quanta la pipeline, con i selettori schiacciando, piuttosto che scrivendo proprio la classe, piuttosto che il div, piuttosto che l'elemento che vogliamo raggiungere, poi possiamo scraparlo e ottenere il nostro file Excel, semplicemente. Vantaggi di questo metodo: sicuramente è veloce da creare, abbiamo la nostra interfaccia, facciamo pochi clic e riusciamo in fretta a ottenere un risultato. Eredita tutto il login del vostro browser, quindi non dovete implementare nessun pezzo di codice per fare login, per salvare la password, perché sta utilizzando il vostro browser esattamente, quindi tutto ciò che è salvato nel vostro browser così sarà salvato per WebScraper.io. Ed è zero code, quindi si riesce a far utilizzare anche a persone meno tecniche, mentre gli svantaggi sono sicuramente il fatto che non parte in maniera automatica, dovete andare lì, schiacciare il bottone e vi tocca, è lento in esecuzione, che comunque c'è tutto il browser, deve aspettare che carica la pagina, deve schiacciare, deve fare delle operazioni abbastanza più simili possibile all'umano, e non si possono fare, diciamo, scraping troppo complessi con delle cose molto particolari, perché appunto alla fine il numero di selettori che puoi avere è limitato a quello che c'è a disposizione, quindi gli scraping troppo complessi potrebbero non essere fattibili con un tool prefabbricato. La prima famiglia di librerie sono gli scraper che si basano solo sull'HTML, quindi non utilizzano effettivamente un browser, ma fanno la query e poi si basano sul codice HTML. In particolare abbiamo Beautiful Soup e Scrapy, che in realtà non sono alternativi. Spesso Beautiful Soup è più utilizzato per il parsing effettivo dell'HTML, mentre Scrapy ha tutta una serie di servizi sia per schedularli, sia per temporizzarli, perché ovviamente c'è bisogno di mettere del delay per far sembrare che effettivamente non è un codice malevole, ma è una persona che sta utilizzando. In particolare Beautiful Soup invece funziona nel seguente modo, come vedete qui un esempio di codice: si va all'URL, proprio si fa una get dell'URL e si prende il codice HTML restituito. Si inizializza il parser e si fanno le get per gli element come in base alle informazioni che si vogliono estrarre. Ricordo che la potenza di Beautiful Soup arriva al linguaggio XPath, che ormai è sempre più soppiantato dal CSS selector, però poco male, è una stringa con cui potete queryare e capire quali sono gli oggetti di interesse per poterli prendere, ed è il massimo, diciamo, livello di potenza che questo scraper vi fornisce. I vantaggi sono sicuramente la velocità di esecuzione, non deve tirare sul browser, non deve caricare il JavaScript, non deve visualizzare niente, si prende il testo e lavora, quindi rispetto a tutti gli altri metodi visti finora è il più veloce in assoluto. E non necessita di molte dipendenze, perché appunto non avendo bisogno di un browser, non ha bisogno di un interprete JavaScript, non ha bisogno di tutto il software che serve per far girare un browser, basta solo la libreria e il vostro amico Python. È facile da automatizzare perché è uno script, potete automatizzarlo in variati modi, ci sono delle librerie, come ho detto prima, per renderlo anche più semplice questa parte qui di automatizzazione. È consente di effettuare anche estrazioni molto difficili, perché alla fine anche quando l'XPath non dovesse bastarci possiamo andare di forza bruta noi di regular expression piuttosto che di fare il nostro codice complesso quanto ci pare. Tra gli svantaggi appunto intanto va scritto uno script rispetto al primo che con 2 clic comunque porti a casa uno scraping, qui un minimo di script lo devi scrivere, quindi un po' più di tempo, e lo svantaggio principale è che appunto mancando di un browser manca di un interprete JavaScript, e questo vuol dire che tutti i siti moderni fatti con un framework moderno senza utilizzare server-side rendering, quindi un classico Vue.js o un React puri, non possono essere scrapati tramite Beautiful Soup, perché si prenderebbe un HTML vuoto, perché il JavaScript non passa per renderizzare gli elementi di cui vuoi ottenere le informazioni. Quindi è una grossa limitazione. Quindi si passa ai tool, alle librerie che invece possono utilizzare un web browser. In particolare Selenium è la più famosa in assoluto. Dal mondo JavaScript vediamo che stanno emergendo moltissimo Cypress, ma soprattutto Playwright, che di recente non è solo per JavaScript ma sta venendo utilizzato anche per Python, adesso ha il supporto anche a Python, è probabilmente il linguaggio che verrà utilizzato di più nel breve futuro periodo, quindi vi consiglio sicuramente, se dovete sceglierne uno, Playwright. In Ruby c'è Capybara, ma poco ci interessa, alla fine l'esempio che vi mostrerò sarà in Selenium, anche se appunto, come dicevo, vi consiglio di andare su Playwright, che è nuovo, è appena arrivato su Python, però sembra un po' il futuro, diciamo. Come funziona qui? Qui bisogna inizializzare il driver, quindi dirgli che driver utilizzare: Firefox, Chrome, un altro browser, un eseguibile a scelta. Il fatto, qui iniziamo già con la configurazione, perché non basta il browser, serve anche un WebDriver che è accoppiato con l'esatta versione del browser che avete installato. Aggiornate il browser, dovete aggiornare il WebDriver e dovete fare in modo che Python li veda. Di default, se è tutto configurato bene, li vedrà senza nessuna configurazione, comunque è possibile specificarli dentro il comando come parametri aggiuntivi, volendo. Possiamo appunto anche specificare il file dell'eseguibile stesso, per esempio per utilizzare un Tor browser, che alla fine è una versione di Firefox modificata, non avremo il modificatore, il WebDriver Tor browser, avremo il WebDriver Firefox a cui specificheremo l'eseguibile del Tor browser e probabilmente il driver che sarà lo stesso di Firefox. Comunque, finita la complessità del WebDriver, abbiamo il nostro browser in cui possiamo eseguire il nostro codice e a questo punto possiamo fare caricare al driver la nostra pagina, fare le find e anche qui abbiamo come potenza massima per estrarre le informazioni XPath e CSS Selector. In Selenium l'XPath è stato proprio deprecato, quindi rimarrà solo il CSS Selector per fare le query. Anche qui più vantaggioso rispetto al tool manuale, sicuramente, e più che altro possiamo scegliere di lanciare il nostro browser in headless mode, quindi non per forza dobbiamo far aprire il nostro browser per procedere nello scraping. Quali sono appunto i vantaggi per utilizzare uno scraping di questo tipo? È sicuramente, come quello di prima, è facile da automatizzare, consente di effettuare scraping di pagine che hanno caricamento dinamico client-side rendered, quindi possiamo scraparci tranquillamente i nostri React, Vue e compagnia bella, quindi siamo contenti. Può essere anche usato insieme a Beautiful Soup, alla fine è una libreria come un'altra, quindi potreste durante il vostro scraping fare dei pezzi di scraping in Beautiful Soup e solo quando vi serve caricarvi le vostre cose in Selenium o in Playwright e tirar fuori i dati che vi interessano. Ovviamente, come svantaggio, come abbiamo visto il primo, è più lento perché devi aspettare il page load, devi aspettare che il JavaScript compili e tutti i classici problemi derivanti da questi. E soprattutto problemi di configurazione, comunque dovete configurare bene il browser, il web browser, sempre accoppiati, sempre aggiornati. UI Automation, che è l'ultimo passo di questa nostra presentazione. Alla fine abbiamo due librerie principali, una Siculix e una PyAutoGUI, e alla fine queste librerie simulano effettivamente il mouse e la tastiera. In particolare PyAutoGUI è davvero una libreria Python, mentre Siculix in realtà è una libreria Java in cui devi scrivere il codice in Jython, quindi comunque neanche chi programma in Java vuole scrivere in Java, e quindi comunque anche in Siculix si scrive in Python. Il vantaggio di Siculix, che noi vedremo adesso, è che ha un IDE molto ben fatto, al contrario dell'altro che, vabbè, ci dobbiamo scrivere il nostro codice classico. Il bello dell'IDE è che ci è consentito prendere screenshot dello schermo piuttosto che le coordinate e soprattutto la parte di screenshot è interessante perché gli posso chiedere schiacciami questo bottone e quindi sarà un po' più resiliente agli spostamenti di interfaccia, fin tanto che il bottone resta quello anche se si sposta non sei proprio loccato sui pixel. E in più appunto possiamo comunque in questo caso simulare come fossimo in un browser, gli possiamo far aprire il browser, inserire la nostra chiave di ricerca e ci consentirà soprattutto di raggiungere quei siti che hanno una bassa accessibilità, in sostanza i siti fatti male. A parte questo si possono automatizzare applicazioni desktop che nell'altro modo non si possono fare e la parte più problematica di un tool di questo genere è l'estrazione dei dati, perché appunto lui ha lo schermo davanti. Si può fare in vari modi, usare il mouse, selezionare, copiare e incollare come faremmo a mano sul nostro PC. E se casomai la selezione non è consentita, si può fare lo screenshot della pagina e poi analizzarsela in tutti i modi più classici, come fare un OCR, eccetera, piuttosto che un sistema di vision per capire bene l'immagine, dove si trova, che cosa combina. È chiaro, molto più complicato che tutti gli altri metodi per estrarre dati, ma ovviamente non era questo lo scopo per cui è stato progettato. Quindi vantaggi non solo web, possiamo automatizzare qualsiasi interfaccia grafica di qualsiasi tipo. Può essere utilizzato per automatizzare appunto i software desktop, quindi farci, come c'era anche un altro talk che che parlava di come automatizzare e creare delle API su applicazioni desktop, questo è anche uno dei metodi per farlo. È decisamente lento perché deve fisicamente spostare nello schermo il mouse, deve come quasi fisicamente schiacciare i tasti sulla tastiera. È difficile estrarre informazioni, come vi ho detto precedentemente, ed è comunque fortemente dipendente dallo schermo. Anche facendo lo screenshot del bottone, comunque quello screenshot del bottone è pixel based, quindi cambiando da una risoluzione a un'altra di schermo, se la risoluzione cambia drasticamente potrebbe non più riconoscere il bottone, perché comunque fa dei confronti pixel based e quindi gli script sono molto meno resistenti rispetto a quelli che si possono fare sul web, durano molto meno. Quindi, prima di passare al vero motivo per cui queste librerie sono state create, cioè per il testing, parliamo dei soliti svantaggi dello scraping. Di solito i siti non è che sono contenti di essere scrapati, quindi prendono contromisure per cui monitorano il fatto che un certo IP sta continuando a fare richieste e quindi c'è il rischio di essere bannati, che il vostro IP non possa più accedere a quel sito. Quindi mi raccomando, se mai dovete fare dello scraping, temporizzate bene le chiamate, fate sembrare al più possibile che quello è un umano che sta guardando il sito. Ovviamente vi potrete sforzare quanto vi pare, ma dopo 20 ore di scraping vi giuro che non è un essere umano. Quindi potete fare un po' tutti i trucchi che volete, ma prima o poi se ne possono accorgere. Quindi anche dividere lo scraping in più giorni è molto utile, così da continuare a far sembrare che è una persona umana a esplorare il sito, e in realtà alcune compagnie accettano di essere scrapate se glielo chiedete. Potrebbero anche dirvi di no, quindi è molto rischioso chiederglielo, però vi potrebbero dire anche sì, va bene, screpa il mio sito, farlo in questi orari dove ho meno traffico, piuttosto che vi potrebbe dire metti questo nell'header, perché soprattutto chi fattura per click, avere un giorno un picco di 1 milione di click e poi un giorno una caduta notevole vuol dire che dai loro clienti che li pagano per click gli dicono ma cosa è successo? Hai perso un sacco di utenti, invece magari era soltanto uno scraper che ha fatto un sacco di click, quindi per loro a livello di statistiche anche solo avere qualcosa nell'header per escludere i click che vengono fatti da una persona vera da quelle di un bot è un vantaggio notevole. È chiaro che non tutti accetterebbero, però alcuni sì. Ma arriviamo sui test. Queste librerie sono state pensate per essere utilizzate per fare test principalmente. E in particolare vorrei fare un attimo un volo pindarico su tutti i tipi di librerie di test. Partirei da quella che secondo me a livello di test di interfaccia è quella più utile, sono i test quelli chiamati spec, che in Python per esempio abbiamo la libreria Mamba, ma ce ne sono molte altre. L'idea è che lo stile è proprio description, it, expect, in modo che raggiungiamo il livello massimo di leggibilità pur rimanendo comunque in un linguaggio palesemente di programmazione. Siamo ancora pieni di parentesi, dobbiamo chiamare le funzioni. Secondo me è il livello massimo che possiamo raggiungere un po' tra la leggibilità e appunto l'essere in Python. Le altre alternative, PyTest è la più nota, in cui i vostri test sono una serie di funzioni. Unit test è quella base di Python in cui i vostri test si trovano dentro delle classi, quindi sono una serie di metodi dentro una classe. Doc test, anche questo molto interessante perché i vostri test sono la documentazione sopra la vostra funzione. E infine Robo Framework, che è il più leggibile in assoluto, praticamente quasi come scrivere in linguaggio naturale. A quel link potete avere il codice di questi esempi di test. Qui come vedete il metodo fastAPI get e gli passi il path, ma sembra proprio linguaggio naturale. Questo è probabilmente il modo più leggibile in assoluto. Ci sembra di essere abbondantemente fuori a Python e ha come svantaggio il fatto che essendo fuori Python quella leggibilità si paga con quello che vedete a destra, che in questo caso non era necessario, molte funzioni esistono già scritte, in questo caso me le sono scritte tutte solo per vedere dove spingersi, però appunto siete spesso costretti, per avere un testo così leggibile, a scrivere molte più funzioni rispetto a quello che scrivereste in qualsiasi linguaggio per fare testing. Quindi personalmente, se riuscite a farlo usare a qualcuno che non è tecnico, tanti complimenti, ci ho provato un sacco, ho sempre fallito. Comunque se riuscite a farglielo usare probabilmente è il linguaggio migliore, così è davvero linguaggio praticamente naturale, però appunto se comunque sono i developer a doverli gestire, tanto vale magari usare un Mamba, che comunque ottenete un grosso livello di leggibilità, pur restando nel codice. Quindi, quali sono i vantaggi? Il vero utilizzo appunto di questi tool, che è già bene utilizzare una cosa per ciò per cui è stata pensata. I test di accettazione e di usabilità sono molto più reali dei test unitari e possono appunto anche mappare bug specifici, quindi potete introdurre nel vostro codice tranquillamente dei test di non regressione, replicando come gli utenti sono arrivati ad avere dei bug, quindi potete registrarli, eseguirli e evitare che il vostro codice domani presenti di nuovo lo stesso bug. Ovviamente c'è da pagare il costo e i tempi di sviluppo sono più alti. Se vi tocca usare un browser è lento, ma in generale anche nel caso in cui non vi serve usare una libreria basata su browser, comunque rispetto ai test unitari sono comunque più importanti. Si prende anche tutti gli svantaggi del tool che avrete scelto. Se avete scelto un tool di UI automation avrete tutti gli svantaggi nel cambio di risoluzione schermo e così via, quindi saranno svantaggi in più. Vi ricordo che quando fate test di accettazione utilizzate quello che in letteratura si chiama test double, per gli amici mock, per appunto riuscire a isolare bene e testare la vostra applicazione e non avere troppe dipendenze esterne che fanno abbastanza male nelle vostre pipeline di CI/CD. Piccola appendice sull'intelligenza artificiale: potete farvi generare i vostri script di web scraping, per esempio tramite ACT di Adept, è un plugin che potete installare nel browser, credo sia a pagamento, mentre ACTGPT è free, c'è il codice online su GitHub, potete appunto testualmente chiedergli di farvi un certo scraping e vi darà il codice per farlo. Il plugin nel browser ovviamente è molto comodo, però si può fare anche in molti altri modi. Grazie per l'attenzione.
Grazie mille per la talk, veramente fantastica. E ci sono due domande su Slido. La prima è: ci sono strumenti per registrare una routine a mano e trasformarla a mano dopo? ClickOps to as code?
Nel senso che volete registrarvi mentre interagite e poi eseguirlo? Sì, ci sono un po' di... intanto su questo punto ci sono vari metodi e anche cose magari alternative. Di solito quando si utilizzano metodi di registrazione, potete sia codarveli che trovare delle librerie già pronte, e io nella vita li ho solo codati se mi servivano, e tipicamente sono accoppiati agli snapshot test, in cui fanno proprio lo screenshot della pagina, quindi puoi registrare il comportamento dell'utente magari anche proprio in produzione per dire quando c'è stato un bug, e registri facendo gli screenshot delle varie fasi, e poi quando lanci test controlli che gli screenshot matchino e se c'è un problema è visibile. Chiaramente anche lo screenshot testing, cioè lo snapshot testing, ha il grosso problema della scalabilità, perché appunto essendo uno screenshot cambiate i colori, cambiate la forma del e i test si rompono, vanno rigenerati gli screenshot e magari vi sfugge che dopo che avete generato lo screenshot non funzionava più. Quindi piano con gli screenshot testing, però possono aiutare tanto, soprattutto quando appunto vuoi vedere proprio quello che fa una persona nel suo complesso e lo registri.
Un'altra è: conosci Wiremock? per fare testing? Se sì, c'è un motivo per cui non è stato incluso?
No, non ho mai usato WireMock.
Easy enough.
Grazie dello spunto, studierò sicuramente.
Non vedo altre domande su Slido, ce n'è una qua.
Non è una domanda. Funziona? Non è una domanda, ma c'è un tool, penso, che possa aiutare per quanto riguarda l'automazione dei test che ho usato quando era all'Intel ed è sviluppato appunto dall'Intel, da uno sviluppatore Intel. Si chiama FMBT. Con questo tu sei in grado di avere la gerarchia completa dei widget che ci sono nello schermo, quindi, o anche finestre, e andare a vedere appunto ogni widget, no? Il nome che c'è interno, ad esempio, no? E quindi anche fare un click o mandargli un tasto, seleziona, ed è estremamente veloce. Perché una volta che tu hai tutta la gerarchia dei widget, no? Puoi fare quello che vuoi. Unica fregatura è con il browser non funziona bene, cioè col contenuto della pagina web visualizzata. Perché in questo caso i browser moderni non creano dei widget di sistema, ma hanno un canvas e quindi quell'area là lo gestiscono loro interamente, cioè disegnano interamente loro. Ma per il resto tipo file, menu, cose, funziona tutto perfettamente.
Interessante.
Abbiamo ancora un po' di tempo. Ok, grazie ancora per la talk.